All right, welcome back, everybody. If you weren't here, the recordings are up. So I think we left off on the SPSS for chapter 8. So chapter 10, yeah. We'll do chapter 11 today. And then we'll start 12 if we have time, but probably won't realistically. So WebAssign should be working. You should have access all the way through chapters 9 and 10, probably assign 11 today. The exam is due tonight by midnight, like 11:59, 2 attempts to take the highest score. Any concerns about how you're doing in the class, anything, you should absolutely talk to me because we have about a week and then a few days, maybe past next Wednesday to take the last exam. So rooting for you all to do well. There is extra credit right here. Chapter 15, there's a quiz. And there's a quiz in chapter 17. But if you do that, you have to forward me the results, and then you need to send me an email directly on top of that, so I know it's from you, because it's through the publisher and they won't tell me who you are unless you send an email. I can use timestamps to know who you are. So I highly doubt you will all take the extra credit at the exact same time. If that happens, I'll email you back or something to say your timestamps are too close or something. So extra credit if you need it. And we were on, I think, in-class activities. And then it would have been, I think, right here. Yes. Yeah. Yeah, they're similar, but they're not in Blackboard. Like points? Yeah. Yeah. On those, I think it's like 1 or 2 shots, I think, but it's extra credit. So I mean, there's, I mean, I can look at that, but I think it's once when it's a third party, so it's possible maybe another time. But like ethically, I want to give you the extra credit because like you know it or you studied it, not because you just like went over it and over it. You know what I mean? And then, of course, the other extra credit is if you go to Rate My Professors and put a review out there and screenshot it to me, 15 extra credit points. Yeah, I hope I'm killing it here. I hope I'm doing a good job. I want you all to be honest, but hopefully you have good stuff to say. I don't want you to, by any means make anything up, but hopefully you're understanding stats. I think we would have left off right about here, 10.4, right? Okay, so 10.4 in your book is on page. The related samples t-test. Yeah, we're gonna do. So if you haven't already started SPSS, go ahead and open that up. Yes. Yeah. I think we. Oh, I mean the calculations on your own. You mean like the last problem and then the SPSS? Oh, sure. You mean like you want me like a brief recap, like maybe like the examples and like how we got there, and then okay, sure. Yeah, that'll help everybody else too. Maybe. I'll go through it because you're asking. I was just curious if anybody else. Yeah, no worries. If one of you wants me to go through it, it's 100% fine. So just right about everybody following along with me. So we're doing related samples or dependent samples. Participants are related. Repeated measure design, they're reserved within each treatment. And then you'll usually have like a pre-test and post-test design. Two types of designs, the repeated measures and matched pairs. Whoa. In the matched pairs design, they're matched based on the characteristics they share. Matched pairs can be attained either experimentally or through natural occurrence. In repeated measures, the same participants are observed in each treatment. Two types of repeated measure designs are the pre, post, and within subjects. And we had some stuff on the PowerPoints where I showed you like some examples of that. I can certainly show you that again if that would help us kind of review everybody. That's right here. Christine. Open. Recent 10. You have to email me the screenshot. So it's www.ratemyprofessors.com and then send me a screenshot. So I can be like, oh, they did it. I apply extra credit at the very end. So what I do is I go through everybody's email one by one, the entire class roster. I see if you email anything throughout the semester. Also to follow up generally if I've responded. And then I see if this is like extra credit subject line, or I see like the quiz. And then I go, okay, based on that. And usually, by the way, to answer your question, Nick, I usually give you the points that you get on the quizzes. And I think there's about 15 in each of those or 17. So there's approximately 30 to 45 extra credit points in the class, which is not going to take you from like failing to an A, like there's no way. But if you're like a half a letter grade or something, or you have a really high B, that might pull you up to like an A. So I know the material is dense, trying to give you a little bit of grade padding, cushion, that sort of thing, so that way do it right in the class. But it can't be 100 points or 200 points. There's like, that wouldn't be right. Like you got to know the material. So let's see if I can pull up example. This. So within groups, between groups effect. So we're comparing them across like each other. And this is stuff we went over on Monday, just trying to give you a brief recap, so it makes a little more sense. Like between groups effect right here, the difference in the scores, like between the difference in the means. So let's go back to our document. So the estimated standard error for differences, or SM, is the estimate of the standard deviation of the sample distribution, or the mean difference of scores. It's how much the estimate of standard error or standard distance to the mean difference scores deviate from the mean difference score stated in the null hypothesis, which is what we were working through. So example one, we said one area of focus in psychology is on education, understanding, promoting reading among children and adults. So we said, let's see what happens if the teacher's in the room or not. So a 6-minute reading session, and we record how much time children spend reading in the session. Here they read with the teacher present. Here's when they read when they were absent. This is the difference in the scores. And then we want to find out whether or not it makes a difference if the teacher's in the room. So we stated our null hypothesis. First, for null, we said there's no mean difference. Spent time reading versus absence of a teacher. Alternative is not equal to 0. There's a mean difference spent reading in the presence versus absence of a teacher. So this is a two-tailed test because we said there's a difference. We didn't say less than, greater than, so it's going to be a two-tailed test. Make sense, everybody, so far? Okay. So set the criteria. So the level of significance is 0.05, two-tailed test. So we're going to cut that in half, it'll be 0.0250. degrees of freedom would be 1, because would be 8 minus 1, which would be 7, because we had 8 people. We had 8 participants, so 8 minus 1 is 7. That's where that came from. So then we locate 7 degrees of freedom in the t-table in C2, and because we're doing a t-test, it automatically actually tells us what that looks like, which is 2 plus 3, 6 is plus or minus 2.365. Does everyone know where I got the 2.365 from? That's in your table. I can certainly pull it up if anyone's unsure where that number came from. Okay. I'm assuming you're good. If not, talk to me or tell me during, before, after class, etc. So this is the t statistic, like the z statistic. So we're going to do the t statistic and then the t obtained value, and we're going to see if anything is different. So what we're saying at this point is we have this, and this is negative 2.365. This is positive 2.365. That, like that. This is retain. This is reject. Checked. This, of course, would be our rejection regions. This is a two-tailed test. We're going to get our t statistic. And that is the plus or minus 2.365. And then, of course, we're going to want our t obtained value, like to abbreviate it like that, or you can write out what it is just so you know. But your denotation is like that. So we want to see on page 314, that's represented graphically if you're following along in your book. Then we want to see what happens. We're going to say there's less than a 5% chance. Remember, if you do something 100 times, there's 5 times you're probably going to hit what you want to hit. That's why we use that off level 0.05. So we want to see if we are going to retain underneath the curve or reject the null hypothesis. So we want to compute the mean, variance, and standard deviation of the scores. Remember that there's no matter whether it's the sign negative or positive, doesn't matter when it's standard deviation, because it's the left or the right of that mean. So the mean of the difference of the scores, or the sum of the difference of the scores, is 120/8, which is 15. Now, where do they get that from? If we go back up here, if you take all these and sum them, I bet you get 120. And then this would be, there's 8 participants, so that's our n, right? So that's 15. To compute the variance, we'll see the computational formula, page 119 on your book as a cross-reference, and you can look at the table on page 315. So what we're going to do is we're going to calculate the sum of the distance of the variance, sum of the squares over n minus 1, with the sum of the squares equal to the sum of the d squared minus the sum of d squared in the parentheses. So the sum of the squares is 3,400 minus 120. And if you're looking at the chart I told you to, that should make sense visually. If it doesn't, just talk to me and we can walk through it in greater detail. It's no problem at all. Minus 120 squared. So that's the sum of the differences versus the sum of the differences squared. But then of course you square it with the formula divided by 8. So you get 1,600 divided by 8/1, 8 minus 1, which is n minus 1, which is 7. So we get 228.57. Now that is just our variance, not our standard deviation. Then of course we're going to square root that, and that's our standard deviation. So then we want to do the standard error, which is a standard deviation over the square root of n. So I'm talking about this formula right here. That's how you write it. You can just remember this is the standard deviation, or SD, for the square root of n. So we did that. We got 5.35. And then we're going to compute the test statistic. We substitute 15 for the mean difference 1 and 0 for the mean difference for the population. Now, the reason we're using 0 is because it's a null hypothesis. We're saying it's equal to 0. Because that's the value we actually literally stated the null hypothesis. You could scroll back up and you would see that it's right here. There's no difference, which is 0. That's where that came from. So we take, so T obtained value, mean difference minus mean difference, like sample minus population, over this standard error for the difference of the scores, 5.35 right here. So that came from. So then you get 2.804. All right, so we have our T obtained value, 2.804, and we have our two values. So what do we do? Do we reject or retain the null hypothesis? Reject. And how is it significant? What happens? The teacher present or absent, if it's on the right side. Do the kids read more or less? Yeah. Yeah. Yeah, that's absolutely right. It'd be less if it was on the other side. Yeah. So the next thing was the calculations with this. Did we do this in class or we could walk through it again, or how are you feeling in the back on the example? What was that? Walk through it? Sure. Yeah, we can do that. So what we can do is, the way I set this up is, and for everybody that's already walked through, is just review, just so it sinks in. So we'll do that, SPSS, and then we'll do 11. We're still totally fine on our pace in the course. So let's go back up here. So first, we're going to want to state the hypothesis. Now, in this case, it's literally going to be almost the same. It's just different data. Because I gave you, like, these numbers right here do not match these numbers. They're similar, but they're not identical. So let's do this one at a time. So we're going to state, we're just going to do this. I'm going to move this down. It's going to look like that. No mean difference spent in the presence versus absence of a teacher. And there's time spent reading the presence versus absence of a teacher. So null and alternative hypothesis is pretty much the same, just new data. Makes sense. So then the next thing we're going to do, and let's all do the math together just to make sure I don't make any mistake in the calculations here. So this should be the same. Yeah, that should be the same. So level of significance, we're using 0.05 again. So we're going to get the same one. Now, if we wanted to, we could change this and then it would be a different number. That we'd look at something different. Like there's a alpha of 10. So with 90% confidence, we can say that something happened. So just for keeping it easy, we'll use 0.05. The degrees of freedom are still going to be 7 because there's still 8 participants, and degrees of freedom is always n-1. Front row, back row. How's that feeling, sounding? Makes sense. What? Oh, lowercase n, absolutely, yeah. Because it's a sample. We're not surveying the whole population of the school. If we could do that, then yeah, it would be the large n. And we wouldn't have to do -1 to account for the sample. But generally, we're going to be working with samples. So again, that's represented graphically on page 314. And the 2.365, do you all want to see where that is? Or does everyone get a sense of where I got that from? Front row, back row, side? Yes? No? Okay. So then the next thing we're going to do is we are going to compute the mean, variance, and standard deviation of the scores. Keep in mind that that's going to be positive negative. So let's just do step 1. And then we'll do the steps just one by one here. So all right, so we need to create basically a table with that data. So let's grab Excel. Open. And then if we go in here and we grab the data. Like that. Oh, that's really, it's like just garbage. Okay. For that, we'll put it in a better spot. And assuming the display will come back on here. Second power. And if technology could just not fail right now, that'd be super awesome. Okay, now that's probably that you can probably see that okay, hopefully. Or you can in a second. So all I did, I took our table and I brought it in. Your D or your difference in scores is already here. I already gave that to you because that's the difference between the means right here. And then I just squared them. So all these values are just squared for Excel. And that's just equals the cell or the number, the shift key, the 6 button to the second power. And I just did fill down. And then for the sum of the differences, I took the differences and just summed them. I got 95. And then I summed these, and for this, the sum of the difference squared, it's all those. So 29, 25, and 95. So now we have the numbers we can plug in to our formula. Is that making sense? And I can totally zoom in if it's tiny on Excel. Is that any? Yeah, that's a little bit better, right? Are you with me so far? You guys need a few minutes to put that in Excel for it to make sense? Totally fine. You should be this, like this whole table, you should be able to pretty much just cut and paste right out of Word. We can certainly make it fancy if we want by going like this, for example. I wrote E because it's like Sigma, but it's Excel. So maybe just give me like a head nod or something when you're. So, okay. For real? All right. Makes sense. So we go back into our Word document. We did that. Okay, so the mean difference is sum of the squares. It's not 120. It is 95. Makes sense where I got that from? So we'll go back to Word. So this is going to be 95. Oh, why is it so small? Oh. 95 divided by 8, because that's our N difference. Basically the same as the sample. So can someone tell me what number you get here? 95 divided by 8? about right. Yep. Perfect. So then the next thing we do is we go back up here and we just did this. So now we want to compute the variance. We want to use the computational formula, which we have all these numbers. So we'll move this back down here. We'll go like that. So the sum of the squares, SD difference. Where sum of the squares is equal to that minus that. So that was 3,400 minus 120. So that's going to be not 3,400, but 2925. 2925 minus 95 squared, still divided by 8. What do we have here? Make sure we're doing our entire numerator and then our entire denominator, or our math will get jacked up. So everyone know where I got that so far? And does someone have a number for me, or maybe a couple people, so that we can see if you're all doing the math right? So if we have a bunch of different answers, then you may want to watch our order of operations.
1,728.
Like that, right? So we're following along. So that's this number right here. And then we're going to do that. We're going to take that divided by 7 minus 8 over 1, right? So that's just like this, 1796.88. Like that. Divided by basically 7. And what do you get? Now, there's a pretty good chance you did your math right, because remember we had 228 before, and I didn't change these much. So if Alexa was giving me a number like 400 or 500, because they didn't change a lot, or 1,000, then we might want to say the math might be wrong. But because it's close and the numbers are very similar, that should be good to go. 255, 256.7, right? I missed a decimal or anything. Okay. So then we did that, and now it's just the variance. Now we need to compute the standard deviation. So we're going to do this. And we're going to change our numbers like that. We're going to put that down here. To compute the standard deviation, we need to take the square root of 256.7. So you can do that with calculator, scientific, TI, or in Excel. What do you have for a square root of 256.02? Perfect. So now we're going to compute the estimated standard error for the difference in scores. So that's 16.02, I think. Right? Yeah, 16.02 divided by the square root of 8. That's still the same n, because it's just same number of participants, and we should have a number right here. Anybody can tell me as you get it, or we can hear from a few of you. It should be pretty close to 5.35, but that's not going to be the answer. What'd you say? 5.66. That sounds about right. Yeah, it was pretty close. All right. So then the next thing we do is we compute the test statistics. So we're going to do the T obtained value, and then we're going to make our decision. But it's not necessarily going to be 2.804. It's probably going to be a different number. So T obtained value, mean difference minus this is 5.66. 5.66. Yes, that's the same thing, right? So the mean difference is the sum of squares over, yeah, PD, which was 95 over. So the mean difference is going to be, mean difference is equal to the sum of differences divided by ND. So let's make sure that those numbers match. So the sum of the differences should be right here. So 95, yep, divided by 8 is, right there. 95 divided by 8 would be what? Yeah. So that'd be the mean, that would be 95 divided by 8. What do you have? 95 divided by 8. Yeah, we're doing the same problem, but it's 95. 11.75, which is right up here, right? That's our mean difference. Did I not write that down? No, that's up here. Yeah. So we're going to grab this right here. So 11.875. So when we come down here, we're going to say not 15, 11.875 minus 0 divided by 5.66. And what number do we get? Makes sense, everybody? See obtain value. So is 2.098 above or below our T statistic, which was what, 2.365? Is that right? Scroll down like this. 2.098, if we did that right. This is 0 because this is your population mean. So this represents your null hypothesis. This is your mean difference sample, which we previously calculated. So we're subtracting the difference. We're dividing it by our standard error of the mean, and we get 2.098. So do we retain or reject the null hypothesis? Assuming we did all the math right, retain, because it's going to be in here, 2.08, 2.098, 2.098. So what problem do we have as a researcher now in this scenario with these two scenarios? Yeah. Because we did the mean difference is equal to the sum of the difference of the mean. So the sum, so that's right here. So the mean difference is equal to this, which is these are the differences between the means. And then we sum them. And then we take that and divide it by the n difference, which is basically still 8. And that's where we get the 11.875 from using that formula. Does that make sense, or did I? So then, because we have 2.098, we retain. So the first time we rejected the null hypothesis, this time, right? We retained, yeah. So now we have one thing telling us that there's no difference in the teachers in the room. But the first thing told, the first set of data told us that there was a difference. So what's our problem as researchers? What is inconsistent? What do we need to do to find out if the teacher is actually helping students do better or read more when they're in their room in this study? Yeah, run another test. Yeah, look for consistency of results. Like, this is incredibly unreliable. We got different results. but it's also fake. I came up with numbers. So, so then the next thing is, yeah, so that was it, right? Yeah, and then it's SPSS. Makes sense? Does anyone want me to walk through any of the formulas, or is it feeling clearer now? We'll jump into SPSS if there's no questions. There are. Yeah, so we would run more tests because we have two different, we were saying retain, reject. We should have 2 retains or 2 rejects in a row, because then we have a little bit more consistency with our results. So we would probably get a different group of kids, a bigger sample, same kids again, but we would do something to see why we're getting 2 different results. All right, so let's do SPSS. Open. We're going to click on the variable view tab. We're going to write the word present and the word absent like that. And we're going to do 0 decimals. I'll do that over here for the Zoom folks. Share. So all I did is I just did variable view, present, absent. If you've been following along in Excel, you could, I think you can cut and paste. I think it'll actually just let you. Let's see if it does that. So you want to go in your data view. So we just go to the variables and then Control V. Yeah, it'll let you cut and paste. But I did not paste that correctly. That's fine. Okay, so removed. I should cut and paste here. Control C, Control V, like that. So you can either enter it in by hand. I can wait for you all to catch up. If you haven't entered that in, and I'll enter that in the other one. Desktop share. Make sure you grab the right data, which is this data right here. Sorry. It'll still work if you have the other data, but this is the data from the first one. Right? Right? Control C. Control C. Control V. It should be 220, 245, 215. 260, 300, 280, 250, 310. And it should be 210, 220. 5. What was that? First graph, yeah. I cut and pasted the wrong one accidentally. I just caught it, so I'm just re-entering it in by hand here. That should be 215. those numbers should match now, except for the 30. That should be 300. Now they should match. Yeah, makes sense. I grabbed the other set accidentally. And then when I tried to cut and paste it, it kept pasting the old one. I don't know why. Are you ready to run a t-test? No. Okay, no problem. You need to enter. Or is it just early and it's stats, Valentine, or you used or okay. So once you have that, you want to click analyze, and then you're going to do compare means, and then you're going to do paired sample t-test right here. And then we're going to move this one right here and this one right there. And then we're going to click OK, and that should just do its thing. Yeah. And that's the numbers you should get, assuming that those are entered correctly. And you see how we got 2.806 like we did before by hand? So like SPS is pretty awesome because it saves you a bunch of time if you know what you're doing. That's literally what we did by hand. You're allowed to use Excel. You're allowed to use SPSS or by hand. Really, you should know how to do all of that by hand, Excel, SPSS, depending on what you're working with. SPS is going to save you time, but ultimately you should still know how to get there with the t-test. Because you might not have SPSS. You might need to do it by hand. There are absolutely real world applications. I literally got thrown a random stats position at work years ago. But then they started screwing with me and telling me that I had to take a second master's program, and then they kept yanking and giving back the free tuition to take the program. So I said, you guys can, I really don't care because I already have a doctorate, so I'm not going to take your other master's course. But that was with the very toxic, one of the very toxic organizations. So, and then just file save as SPV for the output, and then s.sav for the data. And then that takes us to the end of the worksheet minus like some review stuff. Yeah. SAV. Did I say that wrong? I might have. SPV is your output. SAV is your data file. No, I'm just talking about, yeah, you could save Excel for showing your work. That would be fine with the document. I was saying, if you want to upload Excel, you can. Oh yeah, yeah, for sure. Yeah. So like here we're like, so this is going to be like our paired sample t-test right here, save. And then that's only this document right here. But then if we're in SPSS, maybe like this, we can do window. Then you're going to take this in your data file and do file, save as, paired, use something like paired sample t-test. But I would probably just write it out, paired sample t-test. What you don't want to do is it, and then like nothing. You don't want .spv.sav. It'll wreak havoc. It'll cause a problem. It like won't be readable, or it might, but generally it causes a problem. And then this is your extension, your .sav, just like you have like a .exe file or a .doc file. It's just SAV is the data file, extension, the SPV is the output file. And then of course, if y'all want it to be fancy, you could go in here and you could say file, save as, and then you could, that's not right, export, file, export, And then you could change it into, I think it's right. Change options, I think. So you could export it out to a Word file if you wanted. I thought there's usually more options. I guess our version must not be have as many options. Same thing here. We can do file, export now, file, export, and then you can make it into an Excel file if you wanted to. And then you can upload that if you wanted to. But I have SPSS, so just saving it in SPSS is fine. Is that making sense? Clicking for everybody? So just some recap stuff. The mean difference and estimated standard error for the different scores are entered in the formula for related samples t-test. The related samples t-test is computed the same way for repeated measure design and a matched pairs design. The standard deviation of difference in scores is used to estimate the population standard deviation of the formula for Cohen's d, and proportion of variance is computed the same way for all t-tests. Like literally just walked through. Are you ready for chapter 11, or do you need a few minutes or a short break? How's everybody doing? I know it's math and it's early. You need a few minutes? Should we say 5? We should say 10. What do y'all need? Well, I can't do 4:15s because we lose an hour. Because then you're not getting 4 hours of instruction. But 5 or 10 minutes a few times is fine. So if you need 5, take 5. If you really need 10, that's fine. But let's agree on how long we're taking. 5 good, or do you all need 10? You want us to do 7? You want to split it? Rock, paper, scissors? 7.5. Or everybody watches The Big Bang Theory. There's like some really weird version of that Sheldon came up with.
7.5.
Yeah, because if we do 7.5 3 or 4 times, we're only losing like 20 or 30 minutes versus like 15 4 times. Yeah, so we'll do that. So we'll say, unless you guys want to play rock, paper, scissors in the back there. 9:58, 9:59. 30 seconds, something like that. Okay. Well, you always call it 10. Why don't you call it 10? All right. Okay. Grab a cup, whatever you need to do. If you need to run to the restroom, water, ask me a question, etc. I might step out too, but whatever you all need for the next 9 minutes or so. It's stats. Don't you need the break just so it can sink in? Board, want to geek out? No. That was a possibility of the card trick, by the way. Of the chance of getting the card right when we were doing that. Make sure you talk to them about the stuff you guys worked on. Talk to your colleagues in class about that. If you guys were in a group and you have stuff that you didn't have, I'm just assigning you talk to them. What's up?
So she don't know her grade or her age. I would have just used that. You want to? No, yeah, you just say it. Then you'll go down one, and then go back. Go right behind here. Yeah. Yep. And then say that. There's two paths on it. They're the same, but what you want to be careful is you want to drop it, you can do, but if you click on that, then you're gonna save it, get rid of that SPV. And then that's fine. And then we'll just say follow the SPV. Yep.
So yeah, we have this conversation.
And then you should be able to attempts. File. Worksheet. Anything in Excel, sure it works. That too, that would probably be good. More requiring more box. You have Excel. Yeah, that'd be fine. Yeah, absolutely. Yeah. One thing pictures every know is I'm looking for the steps and the map being right. And like talking about that.
That's
Oh, I have but rating purposes, you should really download.
Oh, that's amazing. Most of the time, I'm
So you want to do SPS, you want to do the SPSS, but if you don't have the SPSS, you go to where.
Right.
So this one I watch all for this one. Like, there's a recording of that. For the other one, if it says like a book, something, you can literally go like, stuff will be like, open SPSS, do this, do that. If you just follow the steps of the book, you can get that other part right.
Yeah.
Because like, what I just walked us through, I was literally just like going through the steps of the book. Yeah, so just make sure, so you want to make sure you show your work, so that's why. Word document, like full answers. And then if I have SPSS, the save file, you data file, and SPE file, which is your output. Now, if you completely miss something, I'll tell you, but I'll probably. But what I would do with your response, I would just read through the whole worksheet one more time. What you're about to submit next time. Now, it should almost, so let's just say, you like upload stuff, you're like, oh crap, I should have uploaded that. You just get issues automatically. And I can see it as 1, 2, 3, 4, etc. Does that help?
Oh.
I don't just sit in the back and be like, boundary. And then you have the answers in your Word document. So if you do, if you have any answers. Yeah, I would submit that. Yeah. As long as I can follow the just make sure you will. But if I can't see or read it, then I can't grade you. It doesn't happen a lot, but it Before you jump in. Yeah.
Yeah.
Good.
Yeah.
Good-ish.
Goodish.
That's my club.
Everything good? I think so. There might be, but I don't think I allow that, because I want you guys not to have different screens and just. I want you to like actually know the material. I think there is a way to say like, show me.
Yeah. So
And if
then,
it was anything on the staff,
I,
I would probably
that's
be
my
like, sure. It was like, Gen Psych or
and now
something.
I'm trying to pick up, but
I just-
friend referred me.
There is a way to do
So,
that.
but just say like,
My idea is that you work through it and you do it over and over again, so you
so
understand
like,
like
I'm just.
the math behind it. You don't just go, I
I
don't
got
here's
email.
what I
She wants to send me anything. I told her, like, come in and take it.
The pre- But I think the highest score. So if you tried it 15 times and you got a high score on time one and the low score on time 15, I would still take the highest score. And the pretest, you get all the points ultimately. I go back and give you the points for it. I could play with that as a concept one, that would probably okay with it, because you can study that. I just don't want you to say, oh, it's 2.5.
Yeah.
And then you go through it twice, and then, because the pretest process and the one side, addition of the class, are supposed to actually really enrich your understanding of it. And I decided to like, oh, I'm gonna check a box, I'm just gonna get. I could play with that.
I keep you.
Yeah.
Oh, my God.
I would be down to make that.
I've also been, following
If you get a seat,
the-
like, yep.
This is my friend.
Yeah.
It's tough out here.
There is, and you cannot wait till the end of the class.
Yeah.
You'll run out of time. We have to do it. But for me, especially, of course, this like, all getting the concept, that's so important, especially like the use of that.
Yeah.
But if
And I
you've
will
got-
now-
It should still be open.
No,
If they're not, just cheating or next to the call, I can just. Generally not. That's fine. Website is only 6 attempts, but that's.
Oh, yeah, there's different stuff.
And then
I
can
can
even-
Yeah, I know.
Yeah, I can, extending the due date for PPP
Okay.
on those things for a couple things. I cannot bulk it for the dates that's passed, but if
Yeah.
the points are in there and you have signed, they are going to come out.
Oh, yeah.
So, like, for instance, if we got, where is it? It's just because the system will let me import their release date. And I've agreed with Kevin Tuesday from class and Jeff, we're gonna be able to- getting closer to like 600-700 point mark, when you still have this 4-5, but you still have the test. And then you still have the other tests, like Twitter points, there's just more assignments, it's just more web assignment, but you should obviously have like 100 points. And if you are, you have to follow.
Yeah.
Occasionally I get emails like, I get 4 points, like, which I had to know. So,
No.
because I think it's 170 with class assignments or reports, and then. So basically, like, if you're not in the park, bring it on the switch. If you're doing okay with each of those, you may have a failing, you might have to do it.
You like.
Yeah.
Okay.
Yeah. Just understanding what you're doing. And like I'm telling everybody, if you only. And I will totally do that. So following what you on that, but I'm assuming. I can take it. But if we, to be able to Zoom talk, ready to come in, when I last get. Stop. If your JPEGs are all your watches.
Yeah, and then
Why not?
as we strip it off, it would aside picture it to make it
As long as you get all. Put some other works somewhere else.
So. Yeah, yeah.
I don't know if you guys saw that, but by the way, remember this? You guys remember that, right?
It would have been like that. 151.
That number is likely to be. So I actually did a card trick where I predicted the outcome of the card. This giant number is the number of outcomes, which was correct. I didn't get the correct. That was my own trick like that. But I maybe missed something. It was earlier in the class, like around chapter 5. You might have been out there. 52, because there are 52 cards in the deck. One card to pick out, so that was my sample. N minus N, which would be 52 minus 1, 51 exclamation point. That would be the total number of outcomes that you should get. I don't think that's right. Because I don't think that's, I think the number, I think it's a big number because there's only one sample. Oh, is it right? No. Hang on. Hang on, I feel like I did that wrong. Let me double check something. Yeah, that's right. N, it would have been N over. Yeah, that's right. N. That's 52. That's 1. That's 52 minus 1, which is 50.
So like the probability of you selecting
The card.
specific card.
2 cards per set. Yeah. That should still be a pretty big number though. That should be the number of outcomes, right? The number of outcomes total. All right, so let's do, I think that's like 20 minutes, but hopefully that like got you to a good spot, everybody. Student resources, chapter 11. Oh, cool. This is like the easy stuff. Oh, I've done this for a while, but I feel like this is more straightforward. No. We're not doing a worksheet first.
We might even get to chapter 12 today. Chapter 11. PowerPoint. All right, estimation and confidence intervals. We're going to talk about just a couple things. It's a shorter lecture, so we'll probably get through, like I said, chapter 11. Maybe even we'll start chapter 12. We'll see. Estimation for a one sample Z test, estimation for a sample T test, how we estimate the process of it, estimation for two independent sample T test, estimation for related sample T test, characteristics, the difference between what precision and uncertainty are, which are similar. And then we'll wrap up with how to report it APA style. So we have estimation. This is a sample statistic used to estimate the value of an unknown population parameter. Two ways we do this: the point estimation and the interval estimation. The goal of the estimation is the same as in hypothesis testing. We're trying to figure out more about the mean or the mean difference in the population. However, we're not going to make a decision regarding the null hypothesis, and we're going to estimate our limits within which the population mean or difference are likely to be contained. Now, why might we use a confidence interval? This is helpful if you have more than one scale and they're different scales. If I have a Likert scale of 1 to 7, and then I have another Likert scale of 1 to 5, I can't really just do these tests we've been doing. I need to do a confidence interval because that tells you sort of the range in which is what's happening with the means. So it allows us to estimate, and it is used, like I said, at different scales. So that's how, if you're doing research, you can account for that. You might think, I'm not going to do research, but you'd be surprised. It can absolutely happen in the real and corporate world. Do you all have that so far? Does that make sense? Still a few of you writing stuff down, no problem at all. So point estimation interval continued. Characteristics of hypothesis testing and evaluation. So significance testing, and we say, do we know the population mean? Yes, we stated that in the null hypothesis. Point interval, no, we don't know what it is. We're trying to estimate it. It's a range in that confidence interval. It's between here and here of where the mean should fall. And a confidence interval that's short tells you a lot. Like if there's a small difference between the beginning and the end of the confidence interval, that's going to tell you a lot. If there's a large confidence interval, that doesn't tell you much. You need to run another test or do another study. Large confidence, like, well, it's low to medium to high. That doesn't tell you anything. Medium to high, low to medium, or low, medium, high, et cetera, separated. That tells you more. What is a process used to determine? Well, when we do significance testing, that's the likelihood of obtaining a sample mean. The point estimation is the value of the population of the mean. What are we trying to figure out, or what is learned? Whether the population mean is likely to be correct. That was our significance testing we've done with our Z and our T scores. Point interval estimation, the range of values within which the population mean is likely to be contained. Again, it's a range of where the mean probably is. What is our decision? Well, significance testing, we retain or reject the null hypothesis. Point interval estimation, the population mean is estimated. There is no decision per se. We're just trying to see, like I said, where does it fall? Where does the population mean fall in a range? So significance testing, select a sample mean, determine the likelihood of obtaining that mean if the null hypothesis were true. The result, you learn more about it when you're doing those hypothesis tests. Estimations, select a sample mean and use it to estimate the value of a population mean. And you learn more about the population mean. So same results. Why might we want to do this? Oh, I will wait to see if you're still right. 100%. Fine and okay. Use a sample mean to estimate the population mean. It's an unbiased estimator. We talked about that before. Sample mean will equal the population mean on average. If any of you remember the ESSE exercise where we said take a sample and then it kept falling to the left and right of the mean pretty close. The larger the error was, the further it was away from the mean. Disadvantage of point estimation, sample mean point estimate. You're in no way of knowing for sure it's equal to the population mean because it's an estimate. Interval estimate, population mean likely to be contained. So remember the point estimate and the interval estimate. So that was the point estimation. And then we have interval estimation. This is where the population parameters likely to be contained. Sample of data used to find the interval or range of possible values. Interval estimate stated within a given level of confidence. Confidence interval or range of possible values within which an unknown parameter is likely to be contained. So that's what the confidence interval is. And then the level of confidence is a probability or likelihood. These are different, they're slightly different things here. The confidence interval is confidence interval is something like confidence or CI confidence interval, like a range that we're going to look at. And the level of confidence is the probability. So this is more like I'm going to assert with this much confidence that the range is here. We have examples coming up on the worksheet, but level of confidence and confidence interval are not the same, but they're very closely related. Because you use them like in conjunction with each other. We would have that. No? Good. Not tell me. So point estimation and interval. So point estimate, we're going to estimate the population mean. Interval estimate, we're also going to estimate the population mean. How is it estimated? Well, with the point estimate, the sample mean is used to estimate the population mean. Interval estimate, a range of values, is used in where it's likely to fall. How precise? Point estimate, very precise. It states an exact estimate of the population mean. Interval estimate, less precise because it's a range, which could be equal to the population. Any one in the range could be equal to the population mean. So are we saying like a point estimate, like right where it is, or are we saying it's somewhere in the interval? Process of estimation, 3 steps. To estimate the value of the population mean using point estimate and interval estimate. Choose a sample mean and standard error. We have worksheets coming up where we're going to do all of these things that you're looking at. Choose a level of confidence to find the critical values at the level of confidence. Compute the estimation formula to find the confidence limits. Remember, the population mean is equal to the point estimate plus or minus the interval estimate. Because there's nowhere else that it could fall. I'm either going to estimate it or it's going to be plus or minus interval estimate. But it's going to be somewhere in there. If you start seeing something where like you have your mean and you know what it is in your confidence interval and it's outside of that, that's a problem. It should really be inside the confidence interval. Sample is equal to the point estimate, and then use the standard error to determine the interval estimate, which we're going to walk through the math momentarily. All right. So for example, suppose you select a sample of 100 participants. Your mean was 4, your standard deviation was 5. Your point estimate mean is equal to 4. Substitute your standard deviation is equal to 5 and is equal to 100 into the formula for the standard error. So the standard error SM is equal to the standard deviation divided by the square root of n. So 5, that was our standard deviation divided by the square root of 100 is 0.50. We're going to add and subtract 0.50 from the mean. Then we get our range. You see what that looks like visually. Remember, it's at least 60%, 8%, that's our rule of all possible sample means fall within one standard deviation of one standard error of the mean. And we just calculated what the standard error was. So 3.5 to 4.5 is 1 because it's 0.5 to the left, 0.5 to the right. So we're saying somewhere in the shaded area is our mean square. So you identify the range of values within which population mean is likely to be contained. Estimation for a one sample z-test. In estimation, again, we measure a sample mean and standard error to determine a range of mean values within which we can be confident some fixed but unknown population mean is contained. So we're saying it's. Now we might use that if we wanted to say polls. We want to say how are people voting? Are they liberal, conservative, Democrat, Republican, etc.? We might say assert that the low to medium confidence level people tended to vote this way or that way or have this political opinion. We could also look at how a political opinion might shape a behavioral decision, for example, the confidence interval. These people that had this view tended to be in this range of this sort of behavior based on maybe where they voted for a confidence interval. So there's absolutely practical applications you can use with the confidence interval. So for example, estimation for a one sample z-test. IQ scores in general healthy population approximately normally distributed 100. That's your average, plus or minus 15 standard deviation, and is 100. Our sample mean is 103. Let's see if the IQ of graduate students differs from the general healthy population with a confidence interval of 90%. So the confidence interval, level of confidence. So let's find the 90% confidence interval. What does that look like? And remember, that's the standard deviation. Basically, there's more or less that you can significantly do to the left or right of that 100. So if you're rocking like a 70, you can't do as much as someone with 100. And if you have like 110 30, 145, you can do more, cognitively speaking. Processing speed, like I said, I don't really think that IQ makes sense. I think it's more about your ability to adapt and thrive. It's not. So you compute the sample mean and standard error. Mean is 103. Standard error, here's our formula. Standard deviation, 15 divided by the square root of 101.5. That's where we got that from. That's making sense. Step 2, choose the level of confidence and find critical values, level of confidence. Find the 90% confidence interval. Looking for 90% of the sample mean, surround the sample mean selected, 45% above and 45% below the mean. 5% remain in the upper and lower tail. So you look at the 5% critical value Z table, because 5% and 5% is 10%. And then 90% is underneath. Okay. So if you look this up, your Z-score associated with the 5% towards the tail is 1.645. Why? Because the Z-score between them is 1.64 and 1.65 if you're looking at your Z table. Because we have, I think it's 0.0505 and 0.0495. So right between those would be the 1.645 for the Z. Does that make sense? Or does anyone want to see the Z-score table? Okay. So how did we get there? Let's go into student resources and then chapter 6. I think the Z table is towards the top that I uploaded. This is in the book too. So 1.64. So see this right here, that 0.0505 and 0.0495, that's in our C column. And we're gonna go back towards the Z score. There is no 0.0500 here, but if we were to write it between these two, it would literally be between 1.64 and 1.645, which is why we can agree. And like I said, if that didn't make sense, just tell me again, I'll show you that again, that Z is equal to 1.645. Everybody see that? I can review that if that didn't make sense, or you want me to go slower or walk through it again, just raise your hand, speak up, tell me. If that made sense, the next thing we do is step 3. Compute estimation formula to find the confidence limits for 90% confidence interval. So multiply Z by the standard error. So standard error, 1.645 is Z times 1.5, which is 2.47. Does that make sense to 2.47, everybody? How we got there, or I can certainly walk through it. Then we're going to add that to the sample mean to find the upper and lower confidence limit. So 103 plus 2.47 is 105.47. Subtract it to find the lower confidence limit. 103 minus 2.47 is 100.53. Is that math and where the numbers came from making sense for everybody? We're going to practice in a moment here. Here are your formulas. Alternative to the t-test, estimation formulas. You may want to jot on that chart on the right there. Capital M, sample mean. Small, Greek mu, population mean. MD, mean difference. SM, estimated standard of the error. SM1 minus M2, estimated standard error for the difference. SMD, estimated standard error difference for the scores. Estimation formulas, one sample t-test. Mean plus or minus T times the standard error, SM. 2 independent sample t-test, M1 minus M2 plus T, SM1 minus M2. Related samples t-test, mean difference plus or minus T times the standard error for the difference of the scores, standard mean difference. Example 11.2. Oh, sorry. You good? One sample t-test of examining social function in relatives in individual with OCD compared to the general healthy population. Scores range from 0 to 100. 18 participants, mean is 62. Standard deviation is 20.94. Find the 95% confidence interval for these data. Some of this might look familiar because I believe we did this on our last worksheet, something very similar. So how do we find that? You're still writing, no problem. First, we're going to compute the sample mean and standard error. So we're going to take, so the mean is 62, standard error, standard deviation of the square root of n. Choose a level of confidence, 95% confidence interval. 95% confidence interval corresponds to a two-tailed test of 0.50 level of significance. If you look at your t-table, your degrees of freedom would be 17 because that's n-1. Upper critical value for the interval estimate is t is equal to 2.110. You may want to look at your t-table and just make sure that you're knowing where the 2.110 is coming from. If you're having trouble locating it, I can absolutely pull up the t-table and I can show you where that is. I just need at least one person to tell me if that makes sense from the example a moment ago. Just make sure you're able to find that okay. Or we can do it together. Is that making sense, everybody, so far? So 0.05 plus 0.95 would take us to 1. That's totally why. So the 90 would be like the 0.10, like because alpha level versus confidence interval. So with this, we can say I'm 95% confidence. If you do something 100 times, you're gonna have 5%, 5 times what you want is probably gonna happen due to chance. There is no way as scientists we can be like, I'm 100% confident that this thing's gonna happen, because we have to account for chance. So 95 is typically where we would stop. Technically, you could do the math at a higher level, but typically 95 is where you'd stop. And for the social sciences, it's 0.80, which I know is low. But that's, I mean, 80%, you can still, I mean, you're still serious with 80% accuracy, so like it's still a big deal. But 85, 90, 95% confidence interval a little bit better. So pretty. Step 3, or I can stay on this if people are still. Compute the estimation to find the confidence limits for 95 confidence interval, multiply t by the standard error. So 2.110 times 4.94 is 10.42. So that makes sense, everybody, because we have the t value, we have the t statistic we already had. So we're not doing t obtained value, we're just grabbing that statistic. We're multiplying by the standard error, which we have. And then we're going to add it for the top and bottom of that range. So we're 95% confident that it falls in this range right here. So that means the true population mean score is between 51.58 and 72.42 in this population of relatives with OCD. The point estimate is M is equal to 62. Does that make sense what we're doing so far for everybody? Estimation formula for 2 independent samples. Identify confidence limits with the difference between 2 population means contained. Point estimate is mean 1 minus mean 2. Interval estimate is t times the standard error, mean 1 minus mean 2. So independent variable, speed of eating. Go to the buffet, eat fast, or eat slow. By the way, they give you those very small plates to mess with you psychologically so that you feel bad about going up too many times. So if you're aware of that, you can eat as much as you want at the buffet. Dependent variable is your consumption, number of calories consumed, 12 participants. That's also why the portion sizes are so big at restaurants, so that you feel really full. So you have a good psychological experience, you get the dopamine to release. So that way, like, oh, that was awesome, but it's usually like 2 or 3 times the serving size if you go to the restaurant. Anyways, mean 600 for slow eating group, 650 for fast eating group. Estimated standard error for the difference was 82.66. Find the 95% confidence interval. So in this example, they gave you some of the stuff to run with. So how is that? What does that look like? Step 1, compute the sample mean and standard error. Mean 1 minus mean 2 is -50. Standard error, mean 1 minus mean 2, 82.66. Choose level of confidence and find the critical values at level of confidence. 95% is that 2-tailed test of 0.05, left and right of that tail. Look up in the T table, degrees of freedom is 10. Degrees of freedom is n minus 2. Yeah, I mean, I feel like it should be small n.
Is 12 like?
'Cause it's 12. 12 is the population, isn't it? 2 groups. They tell us. So n minus 2. Degrees of freedom. This can be actually the big N. 2 independent variables. Critical value for interval estimate. T is equal to 2.228. It would depend on how we're looking at it. Are we looking at the population of the people or a sample of them? But for the at this point, the big M is totally fine because of what's coming for chapter 12. For this one, yeah. Why? Because we have 2 different means. We have 2 different means that we're working with. We're not just dealing with one mean anymore. Katie, that's why. That's why it's on -2. Critical value estimate 2.228. Should have that. Compute the estimation formula to find confidence limits for 95% confidence interval. So use this formula. You take T times standard error difference. So T is 2.228. We have the standard error difference, which is 82.66. We get 184.17. So we add that to find the upper confidence limit. So -50 plus the 184.17 is 134.17. And then we subtract it to find the lower confidence limit. So then it would be -234.17 because it started right here. Make sense so far? Or at least conceptually, we're going to do a worksheet in a moment, or we're going to walk through some scenarios. So then we have 2 related samples. Oh, I need to go back. Do that. You're just highlighting, okay. Identify the confidence limits within which mean between 2 related populations are likely to contain. Point estimate, mean difference, interval estimate, T times the standard error. So the 2 different ways in which we would estimate. Point estimate or interval estimate. So we have the example from chapter 10. Teacher supervision, present or absent. Dependent variable, how much time the students spent reading when the teacher was there or not. It's reading sessions, time spent reading, seconds recorded. Mean difference is 15, standard error, the mean was 5.35. Find the 95% confidence interval for this data. Compute the sample mean and standard error. Mean difference 15, standard error, the mean 5.35, choose your level of confidence, find the critical value. You want 95% confidence interval, so that's what you're choosing. It corresponds to a two-tailed test of 0.05, 0.05, and 95, 1. Look in the t-table, degrees of freedom. Degrees of freedom equals -1 for 2 related samples. Upper critical value estimate is 2.365.
What's the degree for?
Degrees of freedom, it should be, I think that should be n-1. Make more sense. I think that's a typo. Yeah, and my degrees of freedom n-1. Upper critical value for the t-value should be 2.365. We can find this in the table if anybody doesn't see this or this doesn't feel easy to find. We can look at that.
And so that like the difference.
Degrees of freedom. Where are you talking? What am I missing?
Oh, yeah, that's simple. That's hiding.
Oh, that. Yeah, that would be. So ND would always be the difference of the sample size, but generally N and ND tends to be the same. And when we're working with it. Step 3. Compute estimation formula to find the confidence limits. Multiply T, which we found by the standard error for the difference, 12.65. Added to the upper and lower confidence limit. We're going to be between 2.35 and 27.65. Does that make sense? So this would be your range because of this right here. So related confidence intervals hypothesis testing. Examples 10.1, 11.4 related samples t-test. Example 10.1, null for time reading when the teacher was absent versus present was a mean difference of 0. Because 0 does not fall within 95% of the confidence interval of 2.35 to 27.65, the same data, we would decide to reject the null hypothesis. So if the null falls within the confidence interval, like that range over here, retain it. If it does not fall within the confidence interval, then you're going to reject it. So very similar to what we're doing with the tails. It's a range confidence interval. We're going to walk through this in math in a moment on a worksheet. Anything else? Everyone have that so far? So characteristics of estimation, precision, uncertainty. Precision determined by the range of the confidence interval. Smaller range, more precise estimate. Longer range, less precise. Certainty determined by the level of confidence. The larger the level, more certain estimate. So rules to determine precision and certainty. Decreasing the level of confidence increases your precision. Increasing the level of confidence increases your certainty. So precision is like the range. Certainty is in which you're like asserting what you think is happening, like 95% confidence interval. So what does that look like? More certain, less precise. So to be more certain, you must give up precision. So we have right here, 80% confidence interval. And see that range is shorter. 95% confidence interval, longer range. So that should make sense between the difference between certainty and precision by looking at that. The more precise, less certainty, more certainty, less precise. So it's, yeah.
Does the CI confidence interval was 80, wouldn't it, the level of significance be 0.2? Or no?
Yes, yep, because that would get us to 1. Yep.
Okay.
Yeah, you got it. Or your alpha level, yeah. At 0.2, yeah, that'd be right. Yeah, absolutely. Have this so far. And then say the level of confidence, point estimate, interval estimate for each confidence interval. So for example, 11.2, we would say social functioning was worse among relatives of patients with OCD. M is equal to 62. Then in the general healthy population, 51, confidence interval is 51.58 to 72.42. You could also, if you wanted to, report the point estimate with the interval estimate in brackets in the 6-minute reading session. Children read longer in the presence versus absence of a teacher. Mean 95% confidence interval is 15, and then 2.35 to 27.65. It's just reported 2 different ways for APA. It's ready to do a worksheet. Is that making sense? Okay. So where we're going to go is, I'll do this for the Zoom folks too. We'll do student resources, in-class activities, and then I believe which means this is probably, nope. Let's check 12. I think that is it. Yeah. Yep. So we're gonna go right here, and then we should have chapter 11 stats review. And then you should have this worksheet. Student resources, in-class activities. And then the folder we're looking for is in-class activities, 71322 part B, and chapter 11 statistics review. Oh, that's not a problem. Try it now. Let's go like that. And then we'll go back here and we will. Did everybody find the worksheet okay? Does anyone need me to come around or assist? Me up here. All right, so let's review some of the stuff we just talked about. Estimation is a statistical procedure in which a sample statistic is used to estimate the value of an unknown population parameter. 2 types: point estimation, exact spot, or interval. It's in a range. Go ahead. Okay. Interval estimations is a procedure with sample data is used to find the interval or range of possible values in which a population parameter is likely to be contained. A confidence interval is the interval or range of possible values within which an unknown population parameter is likely to be obtained. Level of confidence is a probability or likelihood that an interval estimate will contain an unknown population parameter. The confidence limits or confidence boundaries are the upper and lower boundaries of a confidence interval given within a specified level of confidence. FYI, a point estimate is a sample mean difference. The sample mean is used to estimate the population mean. An interval estimate is the interval or range of values within which an unknown population is likely to be contained, like where does it fall? The interval estimate is computed using the standard error of a sampling distribution. A population mean is estimated as a point estimate plus or minus an interval estimate. We can use an estimation to learn more about an unknown population mean by identifying the confidence limits within which the true population mean is likely to be contained. So let's take the intelligence example. 100 mean plus or minus standard deviation 15. Assume we selected a sample of 100 graduate students to identify if the IQ of these students was significantly different from that of the general healthy adult population. So we're assuming maybe because they're getting an advanced degree, maybe they have more intelligence. We can say that with undergrads versus high school, same idea. We recorded a sample mean equal to 103. Let's find a 90% confidence interval for this data. Step one, compute. Let's make sure that we're following along here. Step one, compute the sample mean and standard error. The sample mean, which is a point estimate of the population mean, is equal to 103. The standard error is a population standard deviation divided by the square root of the sample size. Here is our formula in Word, basically. So that was 15 divided by the square root of 100 is equal to 1.50. Does that make sense so far? Choose a level of confidence and find the critical values. So in this example, we want 90% confidence interval, so we chose 90 level of confidence. Remember, in a sampling distribution, 50% of the sample means falls above and below the sample mean we selected. We're looking for 90%, so that means 45% fall below it, the sample mean, and then 5% and it remains in the upper tail and 5% lower tail. To find the critical value in this level of confidence, we look at the Z table in Appendix C, find 0.0500 or 5% in column C, and then we find that gives us a Z score between 1.64 and 1.65. The average of the two Z scores would be 1.645. So that's our cutoff from the 90% confidence interval, where 45% of the data are above and 45% are low or below. The remaining data are 10% of the data in the tails, which equates to the critical value we choose a two-tailed test at a 0.10 alpha level, 5% in each tail. Table 11.4 on page 341 in your text shows the different levels of confidence using estimation corresponding to different levels of significance using hypothesis testing. Everybody with me so far? Is that making sense? You can reference that spot in your textbook. Compute the estimation formula to find the confidence for 90% confidence interval. Because we're estimating the mean in a single population with the known variance, we use the mean plus or minus Z standard error estimation formula. Z times the standard error 1.645. We have the Z score. We have the standard error 1.50, 2.47. By multiplying those through, we're going to add it to find the upper confidence limit. So we add it to 103, 105.47. We subtract it from 103, 100.53. Therefore, we can estimate with the 90% confidence interval that the mean IQ score in this population of graduate students is between 100.53 and 105.47. We are 90% confident that the population means fall within this range of IQ scores because 90% of all sample means we could have selected from the population falls in the range of the sample means we specified. So do your own on the following. A common measure of intelligence is the same here, 100 plus or minus 15. Assuming we have a sample of 120 graduate students, so our n is going to change to identify if the IQ of these students was significantly different than the general healthy adult population. We recorded the sample mean of 110. Let's find 90% confidence interval for this data. So use the steps I just gave you, and then we'll walk through it as a class in 5 or 10 minutes or so to make sure that your math is making sense, etc. And you can certainly ask me questions in the interim. Make sense, everybody? Got a sense? Front row, back row? Cool. What's up? You're absolutely changing the numbers, yeah. I'm changing them right now so we can walk through it as a class. So the mean changes. And the pot and the end changes. Same thing, just like, so the scenario I gave you should give you those to plug in, but it should just be the number of graduate students, which is your N 120, and your new mean, which is 110. Your standard deviation didn't change. I could change it, but I'm just trying to keep it simple for you. Oh, the first one is that we are doing a t-test, and we want to see that. That is a,
Yeah.
we're just getting, yeah, so that's upper and lower mean. So we're estimating, yeah, so it's a related samples t-test.
It
It's-
is. I
Hang on. This is a one sample. It's one sample. You're right. Yeah, one sample. So I had to look. So I don't have everything memorized yet.
That sounds good.
Yeah, she's right. That sounds right from here.
I was just looking at the problem I had, so I think it might.
So you're the front row. Back row? Okay, that's okay. We can walk through as a class. And what about over here? Okay, so let's just walk through it and you can take notes. If it doesn't make sense, just tell me. All right, so First thing we're gonna do is we're gonna do the standard error. So it's 15 divided by the square root of 120. What do we have? Yeah. Sure. Yeah, absolutely. Step one. Yeah, let me like erase and stuff. Yeah. I'll do it on the board simultaneously along with the worksheet so that it makes sense. No problem at all. So step one, we're going to calculate the standard error. So that's good. So step one, calculate standard error. So that's going to be our theta m is equal to this, which is our standard deviation, divided by our square root of n, which is going to be equal to 15 divided by the square root of 120, which is our standard error. And we have a number, somebody, or a few people? What number do you have here? What?
2.25. No, wait, no, 1.36.
1.369 or 1 point? Yeah. 3, 6. We could do 1.37. Yeah, that'd be fine. 1.37. Okay, so we have that. So let's plug that in right here, just so we kind of go through our steps. So we have 1, and rounding's fine. Usually hundredths or tenths. Just be careful when you're rounding, because if you round a whole bunch through all their steps, it might throw you a little bit off. Usually around more towards the end, but this is fine because it's just the hundredths, still pretty accurate. Choose level of confidence and critical values, level of confidence. So really the same thing here. So level of confidence is 90%. 90%. That's your level of confidence. So that's telling us that we have, here's our mean, 45% fall here, 45% fall here, and then your 5% and 5% are in our tails. All this equals 100% or 1. That's what that's talking about. We're going to do a two-tailed test. We're going to look this up. And then you should have a z-score of 1.645. Does everyone know where we got the z-score from? Front row, back row, gentlemen on the left. So the 1.645. It's positive. 645. Or negative. That's the cutoff score. Where 45% of the data are below. We talked about that. Table 11.4 will also show you a sense of that because we do the same thing. Then we're going to compute the estimation formula to find the limits. So we're going to take the mean plus or minus the z-score, which we have, times the standard error of the mean, which we have. So we're going to take the z times the standard error, so 1.645, and then what do we have? 1.37. Does that make sense so far? And then what number do we get right here? 0.25. So are you with me so far? So we're doing z times the standard error of the mean. Sorry, mean plus z times the standard error of the mean. So and then we're going to do the mean minus z standard error of the mean. And this is going to be the lower limit, and this is going to be the upper limit. So we add upper limits, then we're going to have our range over here. So we're going to take 110 plus z times the standard error, which was the 2.25. So this is basically combining that. Make sense, everybody? Where I got the 2.25 from? So then we're going to get 112.25, right? That's our upper limit. So that's going to be 112.25. And then we're going to take the mean minus z standard error. So we're going to take 110 minus 2.25, and we get what, 108.75 approximately? Am I getting that right? 108 point. Yeah, 108. Yeah, that's right. 8.75. It would be the 110 for the mean. Did you pick your own mean? The mean does change, but I gave it to you. So like, we go back up. Okay. If you picked your own, then yeah, then you would have ran with that. So this should be 108.75. Therefore, we can estimate with a 90% confidence interval that mean IQ scores of this population of graduate students are between 108.75 and 112.25, and the mean somewhere within there. We're 90% confidence the population mean falls within this range of IQ scores because 90% of all sample means we could have selected from this population fall within the range of sample means we specified. Does that make sense as a whiteboard help? Are there any steps or anything that you should write here that make that more clear, or is it making sense and everything? Okay. Thank you, because it'll sound good to me. And if you don't tell me, I won't know. So, yeah. We use estimation to learn more about an unknown population mean by identifying the confidence limits within which the true population mean is likely to be contained. So we're saying it's somewhere in here. It's somewhere in here. The estimation formula for a t-test is used when we estimate the mean or the mean difference in populations with an unknown variance. The upper confidence limit is the largest possible value of a population parameter in a confidence interval with a specified level of confidence. Lower confidence limit is the smallest possible value. So we're saying the mean can't be anywhere outside these confidence limits. It's either at the top or the bottom. So social functioning is the ability for the individual to interact or adapt in normal or usual way in social environments. Very important. You can have all the education in the world, but if you don't have any social skills or you can't play nice with others, good luck with the interview and good luck keeping your job. So it's important to have those things. Don't be like one of my bosses that read magazines while he was at work for 8 hours a day. Anyways, in this study, not in this student. Thank you, autocorrect. So tired of your shirt, autocorrect. We record relatives of patients with obsessive compulsive disorder. OCD as healthy as those in the general healthy population. In their study, they recorded the social functioning of the relatives with OCD using a 36-item short survey. 0, worst possible health, 100, best possible health. Sample, or N, 18 participants, we recorded M is equal to 62, and standard deviation is equal to 20.94. If I was writing that, I would say mean plus or minus standard deviation, or I would say 62 plus or minus 20.94. Knowing how that's written is important because on the tests and the exams, it's going to tell you stuff like this, and it might not tell you that the first one's a mean and the second one's a standard deviation. But if you're used to recognizing this, that'll be your cue so that you know. Compute the sample mean and estimated standard deviation divided by the square root of the sample size. So standard error, standard deviation divided by the square root of n. 20.94 divided by the square root of 18, 4.94. Does that make sense? Do you know where I got those numbers from? Step 2, choose a level of confidence. Step 2, choose a level of confidence, find the critical values of the level of confidence. In this example, we want to find the 95% confidence interval, so we chose 95 level of confidence, remembering that in a sample distribution, 50% fall below the sample mean. We find, referring to table 11.4, we find that 95% confidence interval corresponds to a two-tailed test at a point level 0.05 level of significance plus 0.05, 95, I think this is to 1 or 100%. To find the critical value for this level of significance, we look at the t-table. Degrees of freedom are df n-1, so it's 17 for a one sample t-test. The upper critical value is 2.110. So we're going to compute the estimation formula to find the confidence limits for a 95% confidence interval, mean plus or minus t times the standard error. Because we're estimating the mean in the single Population with an unknown variance, we use the estimation formula. To compute the formula, multiply t by the standard estimated error. T times 2.110 times 4.94, because we calculated that, is equal to 10.42. So then we're going to add it to the mean to find the upper confidence limit, 62 plus 10.42, 72.42. Subtract it to find the lower confidence limit, mean minus standard error, 62 minus 10.42, 51.58. 95% confidence interval in the population is between a score of 51.58 and a score of 72.42 on the social functioning measure. Therefore, we estimate with a 95% level of confidence that the mean social functioning of relatives with OCD using the survey is between 51.58 and 72.42 in the population. We're 95% confident that the mean falls in this range because 95% of all sample means we got selected falls in the range of sample means we specified. So now take this new data, new mean, new standard deviation, use the exact same steps as above, show your work, take 5 or 10 to work on that on your own. Do your best with the steps. If you're not sure, it's okay. We'll walk through it, and I'll continue to use the whiteboard and the Word document to walk you all through it. If you have questions in the interim, just raise your hand and ask. Yeah. Because I think I told you, I'm pretty sure. Let me see. We decided to, we chose it in the previous example. So the level of confidence, you can pick that.
Oh, okay, I didn't see it in the thing.
Yeah, that's no problem. So if you changed it, you would have different math. So if you wanted to say 80 or 85, you could.
Oh, wait, so we could choose our.
You can choose your confidence interval, but for the sake of the assignment, I was just sticking with 95% because it's easy to walk you all through it. But if you're trying to figure that out or assert that, if they don't give you the confidence level, you could certainly just grab 0.8 or higher. Generally, we're going to give it should be given to you. Oh, same sample size. So I think I said 100. Did I say 100? Did I even get 18 participants? Oh, I think no, actually you have to count them because it's in the data. I think it's 20, but you might want to double check that or bring that into Excel. So your N is based on the data below. So if you count the numbers in your data points, that should tell you, I believe it's 20, but you may want to double check. Yeah.
The teeth that was like in the last one we used to see.
Because we used the Z. Yeah, we used the T, didn't we? They're both T. Did I type something wrong on the worksheet? They should both be T statistics. It should be T for both. Oh, we found, so yeah, you're right. So we found the first one, we used the Z score M times the standard error. And then this one we used, this was a one sample T, and we did T times standard error, and up here we did Z times standard error. Yeah.
That's my question. Why do we use T for one and Z for the other one?
Because they both will get you to the range, the level of confidence. There's two ways to get there. That's why. I can give you let's see, I can probably give you a more definitive answer here. Hang on, let me just look at this. This was OCD.
Because I did C at first, and then I was like, oh no, I did T, my values were different.
All right, so this one is, hang on, let me just see if I can give you like more guidance on when. So that was a standard error. So that was- I think it's because the formula is actually. Hang on. Just a second. Katie. Because Z is the point estimate and T is the interval estimate. That's why we're doing that.
I gotta write that down.
So they're both estimates. They're just two different types of estimates. Right. They both give us interval estimate.
Point estimate was C.
Point estimate should be Z and T should be your interval. So let's double check that. Should be right there. Estimation for the one sample Z test. And then estimation.
Trying to make it make sense in my-
I know, I'm just trying, because you can use both. Just trying to see if I can. You're just estimating. That's still all right. What's the point? Table 11.4 answers your question, Katie. Because there's one more table in here. Yeah. Table.
There's two different ways to do it. We're usually gonna tell you.
I'm gonna guess.
I'm just trying to
Give you like a really good definitive answer as to when. Both estimates, so I think it just depends on which test you want to use. Yeah. You can for your own understanding, but I'm not requiring it for this one. You might want to though, so you know what you're looking at. Sure. Yeah. I mean, we're gonna walk through it in just a second here.
You find something you want to share with us?
Google said, when you know the population standard deviation, you should use the z-test, and you estimate the sample standard deviation.
So when you know Z, you don't know T.
According to statistics.
I think that makes sense. Because I gave it to you on the example. I'm gonna research that because I want to make sure that's correct for that. Because they're both estimations, it just depends on what the information. But I'm still gonna verify that.
Rate shuts down. I don't remember.
What it's just- You still want to do- Where'd you get what you're adding? Because you would have just added one of the steps here. I think you guys just walk through it. Walk through it. It's all right. We'll walk through it. That's what-
Sample size above 30. Above 30, you can do. Okay, wait, if it's what?
No, you're right, because it's in the book, yeah.
Half.
What you looked up is right. It has to be, it is,
I looked up
what they give us. If they give us, like, for example,
when you know.
we don't know the population, the value of the population variance, that's your t-test.
When, wait, when you know the population standard deviation, you should be tested.
And when you don't know it, then you're gonna,
Yeah, when you estimate. the
when you,
standard
deviation,
you should use the-
t-test. So t-test, we're estimating standard deviation. Z-test, we know what it is,
But they gave us
but
standard
they gave it to us. Hang on.
You know, I'm not gonna confuse myself, I'm just gonna do what the T-score, I think.
They're both estimations. I think we just have more data. I think that they just give us different stuff. Mean plus or minus the z-score times the standard error.
Which you can get with the standard deviation. No,
Because then you know it.
the mean difference plus or minus standard deviation, and this is the error, right?
Statisticshow2.com says the major difference between using a Z-score and a T-statistic is that you have to estimate the population standard deviation.
That makes
So for
sense.
a T-statistic, you have to estimate the population. But he gave us, so I'm just gonna.
I don't think I gave you that, right? Let's walk through this one.
Okay.
And let's look at the difference of like what I gave you, because I think that's where your solution lies. They're both estimation formulas. All right, everybody ready for walking through it? Okay, so compute the sample mean and estimated standard deviation divided by the square root of the sample size. So we're going to compute the sample mean and estimate. So standard error is equal to standard deviation over the square root of n. So that's going to be 7.74. Right, 7.74 divided by the square root of 20, isn't it 20? So what number do we get right here? 1.73. Step 2, we're going to find this. This is not going to be the same. This is going to be 19, right? 20 minus 1. And what is our t? 0.093. So then we're going to compute the estimation formula and find the confidence limits for a 95% confidence interval, mean plus or minus t times standard deviation. So t times 2.093 times 1.73 is what? 3.62. 3.62. And then we're going to add 3.62 to the sample mean on the upper confidence limit, 3.62. And what is our sample mean? I think it's, so that's going to change this. This is 60. This is 60. This is a different number. Yep. And this is 6.38. And this would be 56.38. And 63.62. The 95% confidence interval. This population is between 56.38 and a square of 63.62 on the social functioning measure. We estimate the 95% level of confidence at the mean social functioning of relatives of patients with the OCD using a SF36 surveys between 56.38 and 63.62 in the population. We're 95% confident that it falls within this range because of all the sample means we could select from the population fall within the range of the sample means we specified. And now we are on to SPSS. And that completes chapter 11, and we'll be able to go into chapter 12 today, which is awesome. But we'll take a break. Do you have a question, Amy?
No, I was just like, boo.
Oh. Very, very straightforward. Yep, 9.5 in chapter 9. I believe we might already have that data handy. 9.5, let's make sure, right?
It's on page 286 of the book. For the one sample test.
The social functioning scores, which I think we have. I think we have the social functioning scores right at the very top of our screen here. I'm pretty sure.
Are we using that delta?
Do we have the social functioning scores? Is that right? No, those are my own scores,
Good job. Not you, I'm talking about.
but we could do that.
Yeah.
Going to take it from the text. I'll use whatever Debbie.
Yes.
Which one we use that?
Why don't we do this?
Yes, I have it.
That'd save you time. It's my call, so let's do that. So take your social functioning scores for the second one. It's not going to match the book. It's still going to work though. And then we're going to take the social functioning scores and I'm going to go file, new, and I'll bring those in right here. And then we'll go variable view. Health. HEALTH, decimals 0, Data view. Yeah. Change decimals to 0. Data and then variable view, you want to say health and decimals to be 0. Yeah. So we're going to do independent samples t-test. So analyze, compare means, independent samples t-test. Right? Yeah. Options, 95%, continue. Hang on, options, exclude values. That's right.
Are you sure it's not one sample? I'm pretty sure it's one sample.
I think that's, hang on.
One sample t-test. And then options is 95%. And then let's get okay.
Analyze. Compare means. One of the independent samples.
But this one says 1.5 confidence interval for the one sample.
No, that makes sense. I think you're right. Compare means one sample, health, options, continue, okay. Yeah, let's do that. One sample t-test. So you can cut and paste your data, just health, make it zero it out, and then all you gotta do is analyze, compare means, one sample t-test, move health over to your test variable, options, 95%, say continue, say okay. And then it'll spit all that information out for you. 50.9. We're done with one of them. With the other one. The other one, well, we probably use the same data for the other one, and that'll go fast too. Analyze, compare means, one sample t-test. Move your test variable over. Click on options, 95%, continue through that, click OK and let it spit it out. And then you can. No. Analyze, compare means, one sample t-test, move your health over here, options, just click through that, continue, okay. And then save that. And then 11.9. 11.9. Paired samples. So we can just keep the same thing open.
Okay.
And then we'll just go back to our data here.
Oh, from that one.
Did we just do that one? I feel like that's the same.
That's
Same
the
one.
other one. Fast and slow.
Paired samples. That's the same one. Yeah, that's fine. So just the one we just did, and then we can cut the other one.
Wait, that's not the one we just did.
No, we did one sample.
No, we didn't use that data.
We didn't use that data. So let's hang on. Let's go like
Not that
this.
one.
Let's go like this.
That's not
Yep.
the one we did.
Nope, you're right. No, you're right. You're right. Hang on.
To the right, there we go.
This one. So you go analyze, compare means, paired sample. No, there wouldn't be a reason to do that because that would be, there's no related sample. So we'll skip it. That's fine.
Okay, yes.
Yeah.
You better say.
You guys have to enter more data. Just submit the two. I think I duplicated that assignment from the previous one. Like, because we just did that on the paired sample. The other one, we'll just cut that part of the assignment. You're fine. Yeah, I'm literally gonna say, I'm just gonna delete that from what you have to do. Just do the one. I'll just look for one file that simplifies it. For some reason, I think I was showing that twice. For some reason, I didn't catch it. Just the one we just did with the one sample t-test. Sure, yeah. The one sample, so you did analyze, compare means. And then you did the one sample and then you compare means. One sample t-test. You put your health variable, you said options, you said 95%. Continue, just save that, that's it. The SPV and the SAV file with your data. 2 files, data file, output file, that's it, and we're on chapter 12. Which is all, no, we need it, chapter 12, we have to do a deep dive. So like today, we'll probably just like scratch the surface and then we'll dive headfirst into it on Monday. And then we'll do review, etc. And your final reviews on Wednesday. And then I'll probably say, have the test done by like next weekend or something. I'll give you a few days after the last day of class to do it. From what I can tell, I have a week to grade. I'm going to see if there's more time than that by going and like talking to someone today rather than just like random other professors telling me, because I don't know what they're talking about. So I'm going to go ask the admins how long I have on grades. And if I have more time than I think I have right now, I'll give you more time to finish up the class. I can't do it with, I can't do like 24 hours outside, but I can do like 48. I mean, I can do like real close to my deadline because a lot of stuff's auto graded.
I was gonna do the exam. No, I know, or the presentation.
Yep.
So that was probably like Wednesday.
That'll probably be Wednesday because we probably won't get, yeah, it could be Monday, but I don't think we're going to get through chapter 12 all of that day. We might, but I know how deep I dive in. There's one that's like kind of like, so it'll be like lecture, surface worksheet, and then deep dive worksheet. And that does not usually take only an hour. That usually takes a few hours. So we'll probably finish that mid to end of next class. And then I believe I might even have an exam 3 worksheet review we could do. I have to double check. And then your reviews. And then whatever else we have, if we have any time left over, we'll just review or go over more stuff on our last day. And or we'll go early, depending on where you're at. What's up? You also have to present it because I have a lecture and then 2 more worksheets and I still have like 5 hours and then I have 4 more hours on Wednesday. So that's it. Yeah, this one, that's why we're on chapter 11 and starting chapter 12 today. So we will finish on time. And we probably won't have to rely on YouTube videos. So if you want a few minutes to take a break, and then we'll jump into chapter 12. I'm thinking like 5 or 10, whatever you need. You want to say 10? Say 11:48. Let's go solid 10. So if you want to get a snack, bio break, water, etc., that's fine. And then we'll do chapter 12.
Yeah, they might have.
This is.
Oh, see,
Did you read those books? My mom took me like when we were young. No, 2010, no. I was 8. I read before that. My mom read all the books. You were 8? No, Look, just like my mom took a picture of me that day. Thank you.
Yes.
Yeah, you're right. I'll be fully in it now. It's 3 days. Just a little bit there. I am. I was obsessed with like, oh my gosh. I mean, not in a, I was. Same here. Same here. I did not like it. I don't know. I know. Same. That's how he thinks he looked at the news like the sun. It's so ridiculous, you know, like. Can you imagine the air pressure? Now when it becomes.
Yeah.
His face, you know,
I
like.
have
They have the t-shirt.
I first had the whole page of that by like. Really? Yeah. I don't think that's how it's. Mhm. It was Washington. So weird.
She was angry. I just so much attention. And I was like, you could fix that. I mean, if you can make, like, what she looked like as a kid with the wig, I'm pretty sure it's really gonna be like fake hair.
Wait.
Oh my God.
Oh, no, I lost it. Oh my God, when I saw that though, I was like, this is a joke. No, Alice is.
We have assignments, for set point for chapter 11. Does that make sense? We have to know.
Did I miss that?
Yes.
Where is that? Is that in, is that actually in the folder?
I don't know, it says it's there. Find it.
Oh, worksheet.
Yeah.
Let me see what that is.
I don't know, it's just there in the 10 point. Chapter 11. That's
Mm, I don't know.
Chapter 11.
I don't think that's necessary. Because I feel like I feel like I taught you that.
Worksheet. Click on that.
I got you. It's not there anymore for you.
We don't need that.
You don't need that. I'll double check my point spread on that.
Yeah,
I'll-
it's 10 points.
Yeah, so what I'll do is I'll either add 10 more points to something else to the other one, or if it doesn't, if there's something wrong with the math or something and we have to do it, we'll do it in class and I'll walk through the answers. But, or I'll use that to review towards the end for points. Now, if I add anything that is not already in there, I'll still stick to the syllabus. So that means there could be potentially a few extra points that are there for you. Like, as long as I don't start doing like 100 or plus points that could be extra, we're fine. Because it's not gonna substantially, but for now, we'll just skip it and I'll either add the points or bring it back and then we'll do it together as a class. But I think for time, we should jump in at 12, just so that we're on it. Yeah. I'll come over there. Sure. Yeah.
That was good.
Say the secret word where it is.
I think thing was just way too weird.
You can replace it.
I know, I get it.
But I was saying-
Sign or the meeting
And then I was just
level
reading
was
what
to
your
make it
file
less
says.
tricky. But. No, no, thank you. It's just baby, come on, no.
Yeah, there's a big HCS over there.
It's not just the eight with this.
You didn't even say that, I guess. And now I'm just browse.
She was like, "Yeah, I know you go to CGI."
You should have an SAT. So let's go back to SPSS.
When I look back at it.
And then go hit your actual data file and save it in there. Save it. Yeah, they can. Yeah, that's it. Yeah, it's just easier. Not SAV, not the program, if you type SAV without dot, so those extensions are fine. Just the two dots.
No, it's not.
Usually not good.
I know, I have to do this. It might be big up one. I'm not bad.
right, everybody ready for chapter 12? That's good. It's good. We're laughing. Break it up a little bit. It's awesome. Analysis of variance. Sometimes when you say the word ANOVA, it freaks people out. It just means analysis of variance. So we're going to cover a couple things. Chapter outline, increasing K, shifting up to analyzing variance. Introduction to analysis of variance, which is known as an ANOVA. 2 ways to select independent samples. Changes in notation. Sources of variation and test statistic. Degrees of freedom. 1 way between subjects ANOVA. Post hoc comparisons, measuring effect size and reporting the F statistic. Significant and effect size. And it doesn't get any more complicated than this. It's a good thing it's not a grad course because we'll be talking about 2 and 3 way ANOVAs and linear regression and more stuff, but that's where it stops. So in hypothesis testing, if we're interested in more than 2 groups, the t-tests are limited to testing for differences in 1 or between 2 groups. So the analysis of variance more than 2 groups. See what's going on, like 3 groups, etc. So that's where they came up with that. So we have the F test. We test hypothesis for 1 or more factors, variance among 2 or more group means, or if your variance is unknown, that's when we're going to use the analysis of variance. So remember, variance is how much scores vary after that first score. It's a straight line if there's no variance. Yes, good. Right there, Lona, Gustavo. All right, increasing K, shifting to analyzing variance. How does price affect food purchase? Buffet of foods are made available, healthy, pricey foods, or unhealthy, cheap foods. So we're going to record the total calories chosen. We're going to hypothesize the cheap group will choose a lower calorie meal. Independent sample t-tests, 2 independent sample t-tests. Number of groups, levels of factor K limited to 2. You're going to add a control group, significant difference exists between which groups. So let's do a visual in a moment here. Show you what that looks like. So difference between the samples, K is 2, group is pricey, group is cheap, mean number of calories M1, mean 1, mean number of calories, mean 2. Differences can be only between mean 1 and mean 2. Or 3 independent samples, we can have difference between M1 and M2, M2 and M3, and M1 and M3, or any combination of possibilities. That's why we're doing an ANOVA, analysis of variance. How do the scores vary? What does it tell us? We have more than 1 group. I have some really awesome worksheets that make this so crystal clear that the level of confusion you might be experiencing right now will absolutely go away. I've used them for years at COD, and this is probably one of the hardest chapters, but generally between the first worksheet, which is an overview, which we'll probably do today, and the deep dive, which we'll probably do on Monday, this should feel pretty much okay for you. I know it's might feel like a lot right now, but we will walk through it. So when the number of group increases, so does the number of pairs of group means that can differ, because there's more of them, right? It should make sense. Just kind of keeping an eye. So introduction to analysis of variance, type of ANOVA. Are we going to do a 1-way ANOVA? So we have 1 factor, number of factors, or a 2-way ANOVA, 2 factors. How is observed within subjects design defined in chapter 10. Between subjects design, independent samples, different participants observed at each level of factor. One way between subjects, ANOVA. Remember, ANOVA is just the fancy word for analysis of variance. Most basic, different participants observed at each level of one factor. And we're going to walk back into the example. Like I said, I also have some examples on the worksheets where it's the same thing. I show you the example, do your own based on the steps. I'm pretty sure on this one, I actually just give you the Excel sheet so that you can basically get the ground running on this. Two ways to select independent samples. Quasi-experimental method of collecting samples. Each sample selected from different population, hence the sample constitutes a different group. Or experimental collecting, participants from only one sample are randomly assigned to groups. So just the two different ways we can look at independent samples. So population 1, 2, 3, or K. Or take the sample from the population and put them into groups. This is experimental. This is quasi-experimental because we're not putting them in different groups for the comparison. Remember, experimental, control group, experimental group, a treatment. Quasi-experimental, we're not really modifying or manipulating that independent variable. This next thing you should absolutely write down. It's pretty important. 3 terms. Notation identifies sample size for ANOVA. Small n, participants per group. Large n, population in a sense because it's the total number of participants in your study. So if I said I wanted the gentleman on my left here, the back row, and the ladies in the front, assuming you were all equally the amount of same people, we'd have the same number. The small n would be each of you in each group. The total would be the entire class for your n, and K would be the number of groups 1, 2, 3, for example. Assuming it was equally distributed, we have slightly more women than men in the course, but assuming it was like balanced, this would work. Okay. If you can find these things, it's much easier when you're actually doing the math, just knowing where to look for those things. Sources of variation. One way between subject and ANOVA, 2 sources of variation. Between groups variation, how the scores vary, and the variance of the group means. And then we have the within groups or error variation attributed to error. We're going to calculate these step by step in the coming worksheets, where I literally walk you through it, and then you can see what the F score is and all that good stuff. So what does that mean? Let's look at that visually in a moment here in terms of the differences, so you can sort of really see that, so that I'm not sounding like I think it's not making sense here. So that is your test. Katie, I can go back if the pace is too fast, just tell me. When I see any of you writing, I don't know if you're pulling it up on the computer or you're up here, but by all means, if you're like, hey, slow down, just talk to me and we can walk through it more, or I can go back a slide. So within groups variability, so that's these right here. Between groups variability is right here. So what happens? So between groups is the difference between group means. Within is attributed variability has nothing to do with being different groups. So between groups, we're looking at those means, or within groups, we're looking at like the difference between the numbers, like for your values. And the reason that it's within groups is because versus between groups is we're just kind of looking and we're not saying that the mean's relevant. And here we're saying what's the average. So it's what's happening in terms of like your collective average behavior between the groups is maybe a way you could conceptualize it. those are the between groups. I'm going to walk you through that momentarily. We have our F distribution, which is really just positive. It's positively skewed, called the F distribution table, derived from the sampling to F distribution ratios. The rejection region or alpha level is placed in the upper tail of the F distribution because values farther from zero indicate that they are less likely to occur if the null hypothesis is true. Mean squares and variance. Variance is measured in the ANOVA test. Viewed as mean squares or variance, F statistic or F obtained. So we're gonna do the same thing. We're gonna look up an F statistic and then look up versus the F obtained value with tables as before. And that's gonna be a little bit further down in the table we've been referencing this whole time for our F scores. The mean square or variance between groups divided by so the formula F obtained score is the mean squared between groups, variance between groups, or the variance between divided by the variance within groups. So we're going to have the mean square between groups divided by the variance mean square error within groups. That'll tell us our F value. Definitely write down that formula. You'll be seeing that formula a lot on the worksheets.
So what is that mean? Like on that one table, that would be like. Because on the test statistic, I hate it. Test statistic slide, if you can go back a little bit.
This,
This other thing, right?
that,
Yeah, so like 3, when it says mean squared, at like 3 squared right there, for example.
this is what this right here.
Well, yeah, I'm just trying to understand what mean.
Oh,
squared
mean
is.
square. Yeah, I'm gonna walk you through that, the steps that's coming.
Okay.
You're like a little bit ahead, but that's awesome. Keep asking really difficult, hard questions the whole time. Like that's awesome.
Okay.
But that's coming. So if I explain that now, I probably would confuse you.
Okay.
But that's coming in the worksheet. So we're gonna walk through exactly how to get to that.
Okay.
It's coming up. But that's awesome. That means that like you're excited about stats, enjoying the class, or at least thinking about it in depth, which is important. So degrees of freedom between ANOVA n minus, back to that n minus 1. Degrees of freedom is split into 2 parts, one for each source of variation. Degrees of freedom between groups, DFBG, degrees of freedom between groups, or degrees of freedom numerator, degrees of freedom numerator. Degrees of freedom is associated with the variance for a group means in the numerator equal to the number of groups k minus 1. Degrees of freedom error is I have an Excel sheet where I literally show you what all of these mean with the worksheet. So I think it'll make a lot of sense very soon for everybody. Where I literally start with like raw data and we get the K, we get the N, we walk through it, okay? Degrees of freedom error, degrees of freedom within groups or degrees of freedom denominator. Degrees of freedom associated with error variance in the denominator equal to total sample size N minus the number of groups. So K minus 1, that'd be how many groups you have, and then population of everybody minus K, which is your number of groups. That's your variance between groups and your variance within groups. That's a lot of information. I'll definitely put up for a few before we do anything else. We'll probably do like a problem or two on one of the worksheets today. And that's probably all we'll have time for. And then we'll really dive into it deep on Monday. And we'll finish 12 on Monday.
So the degrees of freedom between groups and degrees of freedom within the same thing. So like the equation would be degrees of freedom, PG over.
Yeah, that's right. Yeah. Mhm. Yeah. That's right. Yeah. Over the error. Yeah, that's right. Yeah, because that's your denominator. Absolutely. Which is coming up. So degrees of freedom between groups always stated first. So for example, one factor independent variable at 3 levels, psych, social, and bio, K is equal to 3. Now, where did I get that from? Back here on this slide. Psych, social, bio, 3 groups, K is equal to 3. That's where that came up. That's where that I got that from. Five students per class, N is equal to 5. There were 5 students in Soc, bio, and psych. Total participants, N is 15. Why is N 15? 3 groups, 5 in each group. That's everybody. That's our whole basically population of each group. Total degrees of freedom, N minus 1, 15 minus 1 is 14. Degrees of freedom between groups, numerator, K minus 1 is 3. And 3 minus 1 is 2 degrees of freedom. Error. N minus K, 50 minus 3 is 12, denominator. So we have 12 degrees of freedom. And then we're going to look this up in the F table, and it's going to tell us what the F statistic is. And then we're going to compare that against the F obtained value. As K, N, or N increase, so does the degrees of freedom. Critical value gets smaller and the power increases. So what we're going to take our groups, we're going to determine what these things are, and then we're going to cross-reference that into the F table. We're going to get the F statistic, and then we're going to calculate the F obtained value based on the information that we have, and then we're going to compare them and tell us, and that's going to tell us what we're going to do with our hypotheses. And I'll keep that up if you're still writing, typing, etc. I think that was the last SPSS exercise, by the way. I don't think I have one for this one. I think that's it. You still want to know it, Colleen. It's still a good job skill to have. It will save you time on a testing environment. Or you can check your by hand stuff in SPSS or Excel. Does everyone have all of this before I go on? Anything else? So one way between subject ANOVA, hypotheses, null hypothesis, group means do not vary. Alternative, group means and population do vary. 4 assumptions to compute a one-way between subjects ANOVA. Normality, that's that bell curve. Assume data sampled from normally distributed populations. Random sampling, assume the data obtained selected using a random sampling procedure. Independence, assume probabilities of outcomes independent or equal. Homogeneity of variance, assume variance in each population is equal. So we're assuming all those things happen with the data that we're working with for us to actually use a one-way ANOVA. Between subject sample size must be equal. So your small n, so if you remember, if we look at that back here. So your number of participants in each group has to be equal or it doesn't work for your ANOVA. So researchers look at employee turnover rates. You quit probably because you usually quit your boss, not your job. It's always the leader that you quit. You're like, this person sucks. I'm going to not work for them anymore. New employees ask how long they expect to stay at a company. employees assigned to groups based on how stressful they rate the workplace. 10 rated high stress, 10 rated moderately stressful, 10 rated low stress. Time employees reported remain at company below, and conducted the ANOVA, analysis of variance, to analyze significant data at a 0.05 level of significance. As you can see, K is 3. Now, why is K 3? 3 groups. N is 30, because your small n is 10, 10, and 10, and 1, and 2, and 3. That's where that came from. You have to go? Go. Okay, no problem. State your hypotheses. Group means do not vary between groups in the employee population. That's your null hypothesis. I don't know why that looks like that on the slide. I'll have to fix that. Alternative hypothesis, group means do vary between groups in the employee population. Set the criteria for the significance. Degrees of freedom between groups is 3 minus 1 is equal to 2. Degrees of freedom error is 30, n minus k, 27. Look up the critical value, which is 3.35, which is in table B3, appendix B. Does everyone see the critical value, or we can look at that together if you don't see the critical value? So this should be 2 and 27. So if we go back into, where's our z-score? Pretty sure we have z-scores up here. Right? Where I downloaded that. All right. So if we go student resources and we do chapter 6 and we click on the Z table and we scroll down, this is, I believe it should be our F table, right? 2 and 27. 2 and 27. 3.35. That's where I'm getting that from. Yeah, so we did the n minus k and the k minus 1. So if we go back to our slide here, degrees of freedom between groups, 3 minus 1, which is 2, and degrees of freedom error, n minus k, 30 total minus the number of groups, 27. So I'm going to say 2 and 27 for the critical value of 3.35. And if we go back in here, so we did 2 degrees of freedom numerator all the way down to 27, and we get 3.35. And the difference, it says right at the top here, is critical values at a 0.05 level of significance are given in light phase type. 1.01 is in bold phase type. So we're looking for a 0.05 level of significance. So that's why it's 2 and 27, which is 3.35 for the critical value. This is your F statistic. So we did a Z statistic and we did a Z obtained value and compared. We did a T statistic and we did a T obtained value and compared. Now we're doing an F statistic, and then we're gonna do the F obtained value and then compare, and then that's gonna tell us something about our scores. Make sense so far, everybody? It's our F statistic for our critical value, which has to do with what we were looking at. So if we go like back to, like right here. So that's your cutoff, your F statistic. And then we're going to see, does our F obtained value fall over here, retain or reject null alternative hypothesis. So the F obtained value, the mean squared between groups over the mean square error. So we have to do the preliminary calculations and the intermediate calculations, compute the sum of the squares, and then complete the F table. I literally have a worksheet where we do every single step one at a time, and that's coming. We'll do that today or on Monday, but I'll walk you through how to do that so that makes sense, because there are absolutely more calculations. Does everyone have this so far? Oh, take your time. It's no problem. Hope not putting anybody to sleep. Hope not losing you guys.
So that's our obtained.
That's gonna be our obtained value. I'm gonna show you how we got there in a second on the slides. And then after you have all these concepts and you have this in the notes, we have a worksheet where we go from scratch through all the steps and how we get there with both examples as well as work we do on our own. Does everyone have that previous page before I go on to this? So these are our preliminary calculations. And where do we get those from? I'll show you. Student resources. That would be probably right here. In class activities. Right here. I believe right here. No, that's not where I have it over here. No, it's right here, I think. Deep dive reference. That's what I want. Yeah, is that right? 3.4. Is that what it says? 3.4. Is that where it starts? 3.4. Yeah. So this right here is literally that slide. So we have. So don't, no, it's fine. It's fine, everybody. See this right here? Do you see this right here? Right?
Yeah.
This slide right here. That's where they reported stuff. And then we got all these calculations. I'm going to pull the exact same thing up on Excel and tell you where they got those calculations from. Okay. And we're going to work through this on a worksheet. Okay. No, I'm just giving you the concepts right now. We're going to do this as a group in class today or Monday, depending on just kind of what we get through. So we took the sum of all of these to get the sum of the values for X. So first, we took all of these and then we just sum the values. Then we squared all of those. So this is low squared. This is moderate squared, and this is high squared. 2.9 G7, yeah. So I squared them all to the left. So these are just values that I squared. Then I took the sum of each of these squares where we got the 119.07, 109.9, and 90.5. And then I also took this right here is the sum of the total right here. So this number, and this number, and this number is this. And then this is the sum of the squares, 319, because 119, 109, 90.5. Yeah, that absolutely makes sense. So that's the sum of, so sum the values, square the values, sum the squares, sum the total of the values, sum the total of the squares. You're going to need that for the preliminary calculations. That's where that's coming from. That's completely in line with this slide right here. That's what they did. They summed and then they squared the sum of the squares. And then they summed the total of everything. Does that make sense what we're looking at? I hope. That worksheet, that Excel sheet will be available, and that's something that we're going to work on in class. So we'll go slideshow from current. So then what we're going to do is we're going to do the intermediate calculations. One, the sum of xt squared over n, 97.10 squared divided by 30. Now, where did that come from? Well, the sum of ext right here, 97.10 squared over n. N is all the groups, so there's 30 total. We get 314.28. Does that make sense, or at least sort of, where I'm pulling that from? And it's not completely out of the air, everybody? Then we're gonna do the sum of x squared over n. So we're gonna take 3430 plus 33 squared, and we're gonna divide them all by 10. Now, where is that coming from? That's these right here. And then we have our small n's for our groups. That's where that's coming from. So 34.3 squared plus 33 plus 29. And then we're gonna take the sum of, and we're just gonna write what this is, the sum of the total square 319.47. Where is that coming from? That is coming from the sum of the total squares. So we took all the values, we squared them, we summed them, and then the sum of all the squares of all those groups is right here. That's where that's coming from. All we're doing is restating it. I have not totally lost you, right? That's making sense? Or mostly, Katie?
I'm like.
Okay. We have a worksheet where we go through this step by step, I promise. If today you kind of have a sense and you start to work through it, you're fine. We're gonna literally dive in headfirst on Monday. You should probably be here on Monday, because this is where it gets the most complicated. I will simplify it and walk you through it. I do it every semester. It's gonna be okay.
Well, I got this.
I'm recording this whole thing.
Yeah, so I can just watch it while.
You could, Yeah.
Just can't respond, obviously.
that's fine. You can zoom in. All of you, as we get close to the end, if things get confusing and you need extra time one-on-one or as a bigger group outside of the times we're scheduled, I just got to know. So far, one of you have been doing that, and that's fine, but talk to me. Don't go home and be confused and come to the final and go, I should have asked questions. A pretty flexible schedule. Compute the sum of the squares. So you should probably write down this formula. And then I'm going to go back and forth with the slides and tell you where this came from. We take 2 minus 1, which is 315.35 minus 314.28. We get 1.07. Where did that come from? 1, 2, 3. So those are intermediate calculations. So 2, 315.35 right there, minus 1, 34.28, 1.07. So we did intermediate, and then we're computing the sum of the squares between groups, the sum of the squares total, and the sum of the squares error. So does the first one make sense? 2 minus 1, this number minus this number right here. Does that make sense so far? Just the first one. Second one, sum of the squares total, 3 minus 1. Same thing. We're going to go back 319.47 minus 314.28, 5.19. Number 2 makes sense, everybody? Sum of the squares error, sum of the squares total. So we have this number already, minus the sum of the squares between groups, which we have, and we get this number. So this minus this, sum of the squares total minus sum of the squares between groups, 4.12. Make sense? Okay. Don't go any further. Just write that. That is absolutely fine. You do not need to know entirely how to understand chapter 12 today. Just have to have a basic sense of where we're referring to stuff. Like I said, we'll jump into it today and or Monday, depending on time. Does everyone have that? Are you still writing? Totally okay if you are. This we want to go slow on because it's got more steps. So we can start to fill this in. We can fill our chart in. Sum of the squares is 1.07. Where did I get that from? Well, that's the sum of the squares between groups. SSBG, sum of the squares between groups, 1.07. Degrees of freedom between groups, K minus 1 is 2. Why? We had 3 groups, 3 minus 1 is 2. Don't worry about this yet. We're gonna get to that. Sum of the squares within groups, error. Well, we have that. SSE 4.12, so we can fill it in right here. Degrees of freedom, N minus K, 30, total people minus K, 3 groups, 27. Total, you would sum these together, 5.19, but it's also 3 minus 1, which is 5.19, which we have. N minus 1 is 29 for your degrees of freedom right here. So 30 minus 1 is 29 for your total. These should add up. 1.07, 4.12, 5.19, 2, 27, 29. Those should add up. If these don't add up, you probably did some math wrong. That's how you can spot check it. Does everyone have that? Don't worry about the F score or the mean square yet. You're good there, Jonathan? Okay. Anybody front row, back row? Next slide. Oh, you're still writing. No problem. So the mean square between groups is equal to the sum of the squares between groups divided by the degrees of freedom between groups, which we have. So we take 1.07 divided by 2, and we get 0.535. Does that make sense, everybody? Or should I go back? Sum of the squares between groups, 1.07, which we calculated right here, divided by the degrees of freedom between groups, which was 2, as you can see on the chart right here, right? Between groups. So we took this divided by this. So we took sum of the squares between groups right here, between groups, 1.07, divided by degrees of freedom between groups, 2, and we got 0.535, which is your mean square between groups. Mean square between groups is equal to that division. Okay. That otherwise. Mean square error, sum of the squares error divided by the degrees of freedom error. Well, we still have that. Sum of the squares error right here, 4.12, divided by 27, within groups error, 27. 0.0512, that's your mean square error. So we're dividing that way. Make sense? F obtained value mean square between groups over mean square error. Well, we have that mean square between groups right here over mean square error. So we divide this by that. Your F obtained value is 3.52. An asterisk next to the F statistic indicates significance or a decision to reject the null hypothesis. Why do we reject the null hypothesis? Well, don't we have an F score up here somewhere? 2 and 27, 3.35 is our critical value. 3.52 is higher. So that's why we're going to reject it. Make sense? So you make a decision, and here's what it looks like graphically. F obtained value 3.52, that's in your rejection region because it's greater than your F statistic that you looked up. So you're going to reject the null hypothesis. So unlike retain, reject, we're just dealing with a positively skewed graph, and we're just looking outside of it. It's just positive, but it still falls in the rejection region. If it was in here, we would retain it. So we're going to reject the null hypothesis. So similar to what we've been looking at, you may want to sketch that out. Okay, over there. Okay, cool, awesome.
So all this was just ANOVA.
Yep, all ANOVA. So post hoc comparisons, you can continue to look at them. That's what post hoc would mean subsequently. Determine which pair or pairs of group means significantly differ. So you conduct the ANOVA, reject the null hypothesis. You could conduct post hoc tests, at least one pair of group means is significantly different. So you'd be comparing the different means. Following your significant ANOVA to determine which pairs or pairs of group means significantly differ. For example, retain the null, hypothesis stop, group means do not significantly vary. So we're gonna do more tests if we reject the null hypothesis. If we retain it, we're just gonna stop right there. Error increases when K is greater than 2. Multiple comparisons are needed. Why? Because group 3 to group 2 to group 1 to group 2 to group 3, there's multiple comparisons between different groups. I can say the back row and compare that over to our 2 guys over here, or to the ladies in front, and I compare the ladies to that, or you, like, there's multiple ways. That's why when K is greater than 2, you need multiple comparisons. If we were doing an ANOVA with the class, but we're not going to. So everyone have that so far? Does everyone have this so far, rather? Post hoc comparisons. All post hoc tests we control for experiment-wise alpha, overall alpha level for multiple tests, conducted on the same data. Default is 0.5 for all tests. I'll range from most of the conservative liberal post hoc tests, most conservative least power, most liberal great power. We're not really going to get into Tukey's and Fisher's test. Those are your post hoc tests. But really, you just know about the ANOVA. These are some other tests, but we're not really going to go into them. It's more just going to be about the ANOVA and the obtained value and the score. It's like if you wanted to do a post hoc test, you would do these. Turkey's HSD is the most conservative, Fisher's LSD is the most liberal. Least significant difference is what LSD stands for. HSD is honestly significant difference. I'll still walk you through it. To compute each for the post hoc test, follow 3 steps. Compute the test statistic for the group means, compute the critical, not radical value for a pairwise comparison. Make decision to retain or reject the null hypothesis for Turkey's honestly significant difference. Comparison 1, so you compute the test statistic for each pair. 3.43 minus 2.98 is 0.45. .30 minus 2.28 is 0.032. And comparison 3.43 minus 3.30 is 0.13. So Turkey's HSD is the mean square error over n. Define Q, we must know the degrees of freedom error and the K, and then we can plug that in 3.52, which we had, divided by the square root of 0.0152 over 10 is 0.43. Oh, that is, you're still over here? No,
No.
right here? Yeah, that's fine. I'll leave it up. So we know how to get the mean square error. We know what our n is based on our each group. So that's where we were looking for the comparison within the group. We're going to do Turkey's SD post hoc. And that's to determine in greater detail what's going on with the differences between them. If we reject the null hypothesis, if we retain it, there is no need to do this test because there's nothing significant to look at. So this is an opportunity to look at between the groups in greater detail. what I'm thinking I might do is I might unlock the worksheets and everything for homework. I'll let you work on them over the weekend and then walk through them in class on Monday, maybe, so that if you wanted to immerse yourself in it, you can. But if it doesn't make sense, you come to class, or I can assign nothing and do it in class. Either way, it's kind of the same. Less homework, but then more in-class work. I will be assigning web assignment, but I'll give you past next class to have it in. Go ahead.
What is QA?
That is Turkey's honestly significant difference. That's just the notation for it.
Okay, no values underneath it. Like, where did that come
So the
from?
mean square error, which we had, is back here. Your mean square error was 0.0152. MS mean square error, and that's what they had, right? Yep. And then divided by 10, which was your N. Where do they get N from? We go back to our groups. And those are the small n's for each group.
Where did the 3.52 come from?
That was, I believe, our critical value.
Oh, okay.
That was our obtained value, not our critical. Our critical was 3.35, our obtained was 3.52. So then they're going to say this is equal to we must know the degrees of freedom, error, and K, which we do. So 3.52 times the square root of 0.0152 divided by 10 is equal to 0.43. And what does that mean? Comparison. So we compare that to the critical value. So low stress and high stress, 0.45. Comparison between moderate stress and high stress, 0.32. Comparison between low stress and moderate stress, 0.13. So we're doing the comparison between each one of them to get there by plugging those in again. So basically what you're going to do is you're going to take the mean square error over the N, but you also need to go to your degrees of freedom. So that's 0.152 divided by 10, which is 0.43. And then you basically just plug it in for each comparison. So you reject the null hypothesis for comparison 1, low and high stress, because the test statistic is 0.45 greater than critical value, 0.43. And then you retain the null for both comparisons 2 and 3, because it's below the critical value of 0.43. Conclusion: employees willing to stay longer if they perceive the work environment to be low stress. So like if their boss is awesome, they don't stress them out. They don't randomly listen to their phone calls and email them disruptively with Outlook, don't know what to say. They stay. It totally happened to me. Super, super annoying. So I had to tell my boss to knock it off. Then he said, that's the only way I can coach you. And I said, well, then I'm not going to perform. And if I don't perform, do that next week. Okay, Mac, you're on. Proportion of variance. ANOVA determines if the group means vary significantly in population. Proportions of variance estimates how much variability in the dependent variable accounted for by levels of the independent variable factor. Two measures of proportion of variance: ETA squared, N squared, or R squared, and omega squared, W2. A little bit of review from before. Similar formulas, just we plug in different things. Leave that up to if we has that. ETA squared. Here's your formulas. Katie, I can go back, or anybody else. Be good?
Yeah.
Okay. R squared is equal to N squared. Sum of the squares between groups, for example, 12.1 divided by the sum of the squares total, 1.07 divided by 5.19 is 0.21. Therefore, 21% of the variability and how long employees stay with the company accounted for by the perceived stress of the workplace. So the ETA tells us our effect size and how much of that variance or variability accounts for how much they're going to stay. We also have omega squared, which is our formula, the sum of the squares between groups minus the difference, the degrees of freedom between groups, times the mean square error, divided by the sum of the squares total, plus the mean square error, corrects for the size of error by including the mean square error, corrects for the number of groups by including the degrees of freedom between groups. Again, just measuring effect size, similar to Cohen's d. But we're looking at variance versus like means here. Sense to everybody? Does everyone have this slide so far? Maybe, maybe not. To summarize results of a one-way between subjects ANOVA test, report the test statistic, the degrees of freedom, and the p-value, report the effect size for significant analyses, summarize means, standard error, or standard deviation in figure or table in the main text of the article. To summarize results of a post hoc test, tell us which one you computed and the p-value for significant results. And that is an overview of chapter 12. Except, oh yeah, we have one more, APA significance. Full summary for results, omega squared as an estimate for effect size, Turkey's honestly significant difference, HSD, as a post hoc test. One way ANOVA reached significance. F227, 3.52, P was less than 0.05, W square was 0.14. Low stress employees stay significantly greater or longer. I think longer would make more sense than greater than high stress. Turkey's honestly significant difference, P is equal to less than 0.5. No other significant differences or evidence. P is greater than 0.05. And that's the end. So what we could do is we could probably take off early if you'd like, rather than jump into the worksheets. And then we're going to walk through the worksheets of chapter 12 in detail. I'm going to assign WebAssign 11, probably due sooner than our next class. WebAssign 12 will not be due until at least after Monday. If I say anything contrary to the announcements, you can remind me, because I'm going to give you more time on chapter 12. And then we're going to do 2 worksheets, including an Excel worksheet, to really dive headfirst into chapter 12 and how to process and do all the formulas. And then on Wednesday, you'll present your chapters 9 through 12 exam 3 reviews. And I believe I have a final worksheet we can do on reviewing for that 3rd exam. Remember, it's not cumulative. And then right now, unless you talk to me before the end of class, exam 2 is due both attempts by tonight at 11:59. It's unlimited time, open book, open note. Don't walk away from Blackboard because it will log you out and you'll lose an attempt. So if mom, dad, whoever, boyfriend, girlfriend, whoever tells you like, hey, I need you. No, I'm in a test. I'll help you later. Okay. Other than that, have a great day, everybody. Yeah. Something like that. Yes. Okay. So what I can do, and remind me of Monday, probably wouldn't hurt. I can make sure questions are late, and then you can just go on to your phone. Zoom app, you can listen to us. Hopefully, you can tell me, since I've had you before, that none of this is freaking you out, except for maybe 12 a little bit.
A little bit.
Okay.
But 11 I like.
Okay. Okay. It's okay. We're gonna jump in and we're gonna literally walk through every step several times. If you want to geek out about it, you're welcome. I have YouTube videos on this, or just come to class on Monday, whatever's easy for you. Okay. Okay, good. So this would be like chapter 12 or like ANOVA. Should be pretty clearly labeled for this chapter. And I absolutely walked through the worksheets and the Excel sheets in that video that are coming up. So like you could like do a preview, because like as a kid, I like to, I always thought it'd be cool to like do time travel. It's not really a thing. But as an adult in my stats course, you can travel
into the future based on the YouTube videos. Yeah, before the class, so. You too. How you doing?
So I've got I think I've got 90.
Let me, before we talk about your grade, let me just stop and,
Oh.
and, no one knows who I'm talking to.